Again, welcome to the NRRA 2025 conference. This is where you pretend like you noticed that someone's speaking in the front. All right, thank you. Again, welcome to our conference today. We're really looking forward to kind of share some of the great innovations that are going on with NRRA and get to meet a lot of people and hear what they have to say. Again, my name is Ben Worrell. I work with the Minnesota Department of Transportation with the MnROAD Research Facility and the NRRA Executive Director. Related to the facility here, enter down there, come this way for lunch and breakfast. There's restrooms out the door here. And if you need to do a meeting or something like that, there's some spaces that you can kind of sneak away in this building here. But again, this is the second year we've been at this facility, and it seemed to work out well last year, so we're back here again. Related to the agenda, again, we do about a day and a half. We'll be here in Shoreview, as you know, going through a number of the teams, looking at the theme of sustainability for the first day here. So we'll go through each team with sustainability, and then we'll also go through each team on kind of some of their current activities that are going on the next day. The MnROAD tour will follow in the afternoon on the second day, and I'll talk a little bit about that at the last session, and I'll kind of go over that agenda and how we're going to handle that tour. Again, tonight we'll be going out to Surly Brewing. If people would like to join us, we can talk more about that. We didn't really publicize it because it is a place where you could drink a beer or two. So we left that alone, but please contact us if you can join us tonight. That would be great. So with that, I guess I'm going to go right into try to go quick on this. But I'd like to give out the 2025 Rohrbach Award. And again, Jerry Rohrbach was a MnDOT employee. He was our director of our office. He worked in a lot of different areas and was loved by many, put it that way. And so this award kind of goes towards the local person in Minnesota that has displayed the traits that Jerry Rohrbach had. So this year, I'd like to say that, let's see, how's this work again? Maria Maston was voted by everyone as the person who accepted this award. And Maria, if you could come up here. If you look in the handout, there's all this stuff about Maria. And I guess I'm not going to read any of this to you. But Maria's done a great job with making concrete what it is today here in the state of Minnesota. She's done all the qualities of Jerry Rohrbach, the traits that he had. And just like to just thank Maria for her work that she's done. And very nice to have you up here. Wait, let's do this. Let's go over this.
Sorry.
We're not good at this yet.
Thank you, everyone. I'm here today because of Jerry Rohrbach. So he's had a big impact on my 30-year MnDOT career, all in materials. When I was a student worker and I was a grad engineer offered a rotation program, and I went to Jerry and I said, I really want to stay in materials. And he said, we're going to figure it out so you can stay here. And so I'm very humbled to receive this award. So thank you, everyone.
The second award that we have is for the Skok Award for Eugene Skok, or Gene Skok as we all know him as. But Gene Skok was an instructor for many years, kind of a mentor for many of us here in the room that grew up here in Minnesota. And this award was set up to be kind of a lecture, the part of this conference. And it'll be, this contributes to the national kind of things that we're doing with pavements in the United States, contributions to pavements in the United States. Again, this year's recipient, you can see the last few years, is Khazanovich from the University of Pittsburgh. Lev, come on up here and let's thank Lev for his work. Lev has worked in the area of concrete pavements and has done a lot for the state of Minnesota when he was here at the University of Minnesota. So, let's see.
Thank you very much. I'm I'm really honored to get this award. Zhan was a remarkable person, a great engineer, a great researcher, a friend, a mentor, and a colleague. I deeply admire him, and I would like to thank MnDOT and the National Road Research Alliance for this honor. Thank you.
Want to do that one? Where did you go? Right here.
Well, again, thank you for the opportunity to give a Zhan Skok lecture today. First, I would like to tell you that it's great to see so many familiar faces in Minnesota. I'm out of the state for 8 years, but I still consider it as a home state. I would like to send you greetings from my friend, Professor Julie Vanderbush. She received Jerry Rohrbach Award in 2017. Shortly after I moved from the University of Minnesota to the University of Pittsburgh, and I was wondering if partially she was recognized for helping to liberate Minnesota from me. But anyway, we are very proud that the University of Pittsburgh is the only organization outside of the state of Minnesota that has both prestigious awards. One of the legacies of Zhan Skok was his mentorship of many generations of pavement engineers in Minnesota and across the country. So I consider this award not as an award for my modest personal contributions, but a tribute to many great students I had a privilege to work with over 14 years at the University of Minnesota, and after that, for 8 years at the University of Pittsburgh. The title of my presentation, it's a great time to be a pavement engineer. So in the next 30 minutes, I'll try to explain why right now it's a great time. Although, like for me, it's always been a great time to be a pavement engineer, but now it's a special time. But let's start with defining what pavement engineering is. In my pavement class, I would like to start my course with a slide that I adapted from great Carl Monismith. It shows that pavement engineers deal with a wide range of very, very complicated and important problems. And to solving them, it requires a deep knowledge of material science, engineering mechanics, computational mechanics, mathematics, computer methods, mechanical engineering, and many other areas. And that makes pavement engineering truly interdisciplinary field. But many people, especially in academia, think that payments are a low-tech field. And I can't blame them, because 35 years ago, I was one of them. Again, I was trained as a structural engineer in the former Soviet Union. And when I applied for a PhD study at the University of Illinois, I wrote in my application that I would like to do research in concrete structures. But I was accepted into a concrete pavement engineering program. I was confused and decided to consult dictionary, not realizing it was a British in dictionary. And the dictionary told me that pavements are sidewalks. I was confused, but decided to give it a chance. Well, University of Illinois was fantastic. I was trained by my thesis advisor, Professor Tasos Ioannidis. My professors were Ernie Berenberg, Marshall Thompson, Mike Darter, Sam Carpenter. Many of my classmates like Jeff Rossler, Tom Van Dam, Navgard are industry leaders today. But the subject felt quite strange. In the first year, I was taught that to design a pavement using the empirical RC design method, what you really needed was a straight edge and a sharp pencil. In '93, this procedure was significantly improved by adding a straight line. There was a Westergaard model, but it treated a concrete pavement as a plate on a Winkler foundation. So simple structure, at least how I thought at that time. We were told that a critical loading on a pavement is a wheel edge loading that generates high tensile stresses at the bottom of the concrete slab. And there was simple analytical solution for this. Of course, daily variations in temperature were making the situation a little bit more complicated. So during daytime, the slab would curl up and generating tensile stresses at the bottom, which structural engineers still confused why this way. And at nighttime, it reverses, and we get tension at the top. But we were told that daily gradients in temperature are higher than nighttime gradients in temperature, so tensile stresses at the bottom are still higher than the top. So cracking would only initiate from the bottom and propagate up. When I was asked at the end of the first semester if I still would like to continue a PhD study in this field, I was told, yeah, it seems to be interesting, but I was wondering if there would be enough problems for the entire PhD thesis to analyze the simple structure. My professors assured me that it wouldn't be a problem. And 35 years later, I can see that they were correct. A bulk of my research dealt with development of finite elements tools for analysis of concrete pavements. I was improving a computer program, ILLASLAB, developed by Professor Berenberg and his student Amir Tabatabai in the end of 1970s. And this program was later improved by many graduate students at the University of Illinois. And I made my modest contribution to the program. And by the end of 1990s, it became quite powerful, although very difficult to use tool. So when I joined Nichols Consultants, that later became Applied Research Associates, we decided to upgrade this tool, and we approached MnDOT and Michigan DOT, and they joined the efforts, and we developed a new tool, a computer program, iSlab 2000, that was probably the state-of-the-art tool at that time, and has been used for 25 years on various important projects around the world, and it was used in the development of the mechanistic empirical design guide. But the first and probably the most memorable project when this program was used for real-time application was an analysis of I-80 failure. This section of I-80 was reconstructed in 1993. It used ASHTA 86 procedure at that time. It ended up to very thick pavement, 13-inch thick. The design life was 40 years, but transverse cracks started developing in a few years. Numerous studies demonstrated there was no thickness or strength deficiency in that pavement. But the number of cracks kept increasing. And what was really strange, that pores clearly indicated that cracking initiates from the top and propagates to the bottom. That was strange because, according to Westergaard theory, it could not happen. Transverse and longitudinal cracking were supposed to initiate from the bottom and propagate to the top. We just finished developing of iSlab when Ares was asked to investigate this problem, and we collected all the information we could about this pavement, its thickness, strength, material properties, temperature gradients, and perform comprehensive iSlab 2000 modeling. We conducted hundreds and hundreds of simulations. Now we could do it, and now we could easily visualize the results. But in spite of some minor improvements, the results clearly confirmed the Westergaard theory. Stresses at the bottom were always greater than stresses at the top. So we improved our model. So instead of modeling just one axle, we modeled placement of the entire track on the pavement for nighttime conditions. It didn't make a significant difference. It's made the results a little bit closer, but still the bottom stresses were higher than the top stresses. And at that time, Dr. Darter came from Chile, where he took this photo, now iconic. You can see a shadow for this string, but the photo was taken during daytime. Otherwise, you wouldn't be able to see it. And at daytime, the slab is supposed to curl up, but it behaved as it is at nighttime. So we looked in the literature and found some research at Technical University Munich, where we found, this phenomenon was explained by two processes: an irreversible shrinkage and temperature gradient during solidification of concrete immediately after placement. So we performed kind of a quick assessment of this phenomena and introduced built-in kernel temperature gradients, a temperature gradient that required to make the slab flat. And when we accounted this in the analysis, we were able to predict that stress at the top surface can be higher than the stress at the bottom surface, and cracks can propagate from top down. And it was the end of 1990s. At that time, we were already working on the development of the mechanistic empirical design guide. And the process started in 1987, before this project was completed. So we felt that this finding was so important that we approached CHRP and told them that we will include top-down cracking into our models, because otherwise thick pavements would not show any cracking, which is not really the case. But that made a problem of predicting critical stresses for the mechanistic empirical design even more complicated, because stresses in concrete pavements depend on many factors: traffic loading, axial geometry, axial weight, load position, how far it's placed from the edge, temperature gradients, now moisture gradient, material properties that change with time, subgrade properties that change seasonally, slab thickness, joint spacing, base type, presence of shoulder, and many other parameters. So you see this slide many times. This is a framework of the mechanistic empirical design guide that was developed like more than 25 years ago. And my job was to develop a structural model. We could not incorporate iSlab directly into the program. It would take hours to run it, because Mike Darter wanted to implement an incremental damage approach that required computing stresses from every axial load application for every temperature gradient over the pavement life. So what we've done, we looked into machine learning. So how to develop a model that will predict the stresses almost instantaneously, but be accurate at the same time. This problem would be very difficult even now with modern computers. In 1990s, I believe we had P60 or P100 desktops. So we were running them for several months continuously, but even that would not allow us to develop brute force models. So we were looking for something else, and we developed the so-called similarity concept that allows to compute stresses in one structure if stresses in a totally different structure are known, if certain conditions are satisfied. And we call it similarity concept. And we developed a mathematically rigorous condition for the similarity. I will not go over these equations. I just would like to point out one parameter, a Karenev non-dimensional temperature gradient that combines 7 independent parameters into one factor. I found this parameter in a Russian book where it was given without any explanation as a self-evident quantity. But we checked it, and it really works, and it allows us to develop neural networks that matched iSlab 2000 very closely. And that allowed to develop a very efficient procedure for design of concrete pavements. If you remember, some of you may remember when that time it was called 2002 Design Guide. It was introduced. A single asphalt design took like more than an hour, and concrete design took a little bit more than a minute, and most of them was consumed by climate simulation. So I'm very proud of the work we performed 25 years ago. That's mean that it can be improved, and I'll show you some improvements today. But it was, in my opinion, it was a remarkable achievement at that time. And Mike Darter, who led that effort, made an enormous contribution to the field. Well, after the guide was completed, I moved to Minnesota when I had the privilege to work on many projects sponsored by MnDOT and NCHRP, Department of Energy. There were many great projects, and I was privileged to work with many great students. But today I will mention only a couple projects. Yes, the design guide was great, but if you look just at how many inputs the users should provide for a single design iteration, and in many cases, the user doesn't have the knowledge what inputs are required. What this mean? Inputs mean. That creates the tool very complicated, and the license also is very expensive. And this is one of the reasons why the guide hasn't been completely adopted even 25 years after it was completion, although it was voted by APTech in 2008. Many states adopted it, but not all of them. So when MnDOT approached us and us to develop a simplified tool, we again looked at the machine learning and developed that time first version of MnPave rigid, and Derek Tompkins, who is in the room, will present on that subject later today. They've done a fantastic job on this project, and this tool allows to get a result that match exactly at that time APTech version 1.1. For a fractional cost, it's a computational cost. It matches exactly for level 3 design inputs for Minnesota the conditions, and it can be freely used. And later, when we moved to Pittsburgh, we developed a similar tool for Pennsylvania conditions. So you can see MnPave. So basically, what we've done, we took these inputs identified by MnDOT. We ran a very extensive simulation of APTech 1.1 software, collected fatigue damage, and using analytical extension, computed slab cracking, and from that we were able to determine required slab thickness. For PennDOT, we used the same approach, but now we used pavement emit version 2, and we include a little bit more factors, and the program not only computes the required slab thickness to combat cracking, but also determines the required dowel diameter to prevent excessive joint faulting. And in addition, it's also predicts development of cracking and faulting over time explicitly. Okay, these are simplification of the design guide, but it does mean that the design guide doesn't have limitations, and one of them was identified long time ago, is the way how mechanistic empirical guide models interaction between concrete slab and a base, especially if the base is stabilized. For an aggregate base, it's not an issue, but for a lean concrete base in particular, the loss of bond is the most important parameter that controls predicted cracking. On top of it, according to the pavement ME even 2.6, replacement of a aggregate base by a cement treated base should always reduce cracking. But in the LTPP database clearly indicates that it's not the case. And in many cases, lean concrete bases perform significantly worse than aggregate bases in terms of cracking. So we were lucky to win an NCHRP project 151, and Derek Tompkins and I developed a new tool. Of course, we looked at the interaction between the base and the concrete slab, and we introduced a partial bond and an ability to vary this bond over time and deterioration of this bond. But it did not help to improve predictions significantly. So we looked at the entire procedure and we modified the stress analysis. We looked at the temperature linearization. We modified damage calculation, modified cracking prediction. So basically, it's easier to say what was not changed than what was changed. It's a really new procedure. After the project was completed, I performed a detailed fracture mechanics simulation of the concrete slab, and we found that the new model actually much closer to reality than the old one. But I would like to point out another parameter that was changed is built-in curl. When we introduced it in the end of 1990s in the United States, first reaction was no, that's not correct. But in 2 years, it was accepted as a ground truth. And if you go back to understanding what's the causes of built-in curl, it's one of the causes is non-uniform hydration of the concrete slab. But we are pavement during the entire day, sometimes for a week. So our conditions in which concrete solidify are not constant. So there is no reason why one number can explain the entire phenomena. So at least temporarily we introduced a model that accounts for this effect that requires kind of two parameters. The user still inputs only one number, but it's depending on the base stiffness, it converts into two numbers, and it allows to make much more accurate prediction for the base type, both aggregate base and cement treated base. We still had problems with permeable asphalt treated bases, but at least these two type bases were taken care of. This model has been implemented in Pavement ME version 3.0. So if you run this model, you should be aware that it's drastically different from 2.6. It's not just minor update, it's a different model per se. And so this is an example how the same neural networks that were developed 25 years could be adapted for totally new conditions if you change analytical extension. But there were several other projects where we had to develop different machine learning techniques. We developed a tool for early opening of concrete payments to traffic based on a project sponsored by NRRA, and Bernard Zwichai was a project manager for that study. And again, in that project, we simulate stresses and concrete and deflections in concrete payments immediately after concrete placement and opening to traffic. This is different from Pavement ME that assumes that concrete at least a month old. We developed a new procedure for unbonded overlay design as a result of pool fund study when Tom Burnham was a project manager and Julie Van der Bush was a co-principal investigator. And again, that requires different machine learning because the structure is quite different. So we use different slab model to simulate. So basically, over 25 years, we developed a variety of models, and we use machine learning quite extensively for solving very complicated engineering problem, making it transparent to user. So basically, user can concentrate on engineering problems and not on performing calculation. And it was quite satisfying. So I was very happy where I was. So I had an opportunity to deal with very important problems and develop quite interesting solutions for them. But something happened a little bit more than 2 years ago. So as I said, again, it was always been a great time to be a payment engineer. But 2 years ago, one of my students introduced me to generative AI. So many of you familiar with ChatGPT. It's a totally new tool, totally new technology. It's based on transformer architecture. It trained on a vast amount of data, not necessarily all of them related to payments. Actually, the majority, they're not related to payments. And even right now, LLMs are not very good in payments if you start asking really deep questions. But it can really change the world. It accelerated progress in many fields like healthcare, material science. So it did not take too long to my students to convince me that it can change pavement engineering, and I agree with them. Just a few features of large language models. They are based on the concept of embedding. So pre-trained models take words or sentences and convert them into vectors, and it preserves not only the meaning but the content of context of the word. So, for example, if you have developed like fall protection, if it properly converted, the model understands that it's similar to safety, harness, and so on. Similar with the sentences. So it can, if you're talking about injured worker, it understands like similar content to this. Large language models it's a totally different mechanism. So they based on probabilistic predictions of the next word using mechanism of self-attention. And so basically they can predict next word based on the previous words. We are not we've just started doing research in this area like about 2 years ago, but in my opinion, it's already got some exciting results. For example, we use it to identify major causes of construction accidents. The Department of Labor collects data on all accidents that resulted in hospitalization. We extracted accidents related to highway constructions, and we converted them. We vectorized them, and after that, classified them, and it allows to develop a little bit better understanding what are the major groups that we develop classification that better matches narrative described in the database than actually classification performed manually, and it allows us to kind of develop hierarchical exploration. For example, like 20% of accidents related to fall, about 50% of that accidents related to fall on the first level, and only a quarter of them is from the second level or from the ladder. It was our first application of this technology, and now we're working on AI safety assistant. So the tool that will help safety officer to come up with daily instructions to construction crews based on specific operations that the crew is supposed to perform. And we're taking the best practice manuals from MnDOT or developed by Department of Labor, and we also take into account past accidents from the Department of Labor database. So, and in this case, we'll be able to provide specific recommendations based on the technology, and this recommendation will be done in an interactive manner. So the assistant is supposed to ask the safety officer exactly what operations are supposed to be performed, with what materials they're going to deal with, what instrument they're going to use, and come up with the best recommendation. In the unfortunate event of an accident, the tool is supposed to help the safety officer to develop a report that is consistent with the Department of Labor requirements, but asking follow-up questions, what actually happened, and so to collect in a simple way all the information required for the accident and avoid the need to manually select numerous categories that are currently required in this report. We're currently also working on automated analysis of public comments. MnDOT periodically collects comments and constantly collects complaints from the traveling public, and they provide usually textual form, and after that people had to manually go and categorize them and analyze it. So in our case, we took 925 complaints, or actually comments, for the Pittsburgh region, and we categorized them and clustered them and divided in the groups. And after that, for each group we can develop like what's the common complaints and separate. And now we're separating complaints that requires immediate assistance from like long-term planning. But there is also, as a byproduct, we allow a very simple way to visualize what in each group of the complaints are. Well, in my opinion, and finally, I don't have a slide, but we're working on the tool that will take MnDOT's design manual, best practices from other the states, like from CP Tech Center, and develop an assistant for payment designer or payment planner. So basically, we'll be able to extract all the relevant information and provide the best recommendation on design or construction of concrete payments. This is actually a very difficult task because the current large language models are not very good with facts, and if they don't know something, they try to invent. That's where the strength is. Everything is probabilistic. So, but we need the exact answer. We don't need the depth to guess. And another problem is that we can't use like GPT or Gemini, because as soon as they make an upgrade, everything what was done before kind of goes away. So we're using local open source models that we have full control on. If there is update, we can check if it affects our results. But it's a huge task, but it's exciting, because if computers can play chess better than human, they should be able to assist payment engineers to do his work like really well. And it sounded like a science fiction a couple of years ago, but it might be a reality pretty soon. It is an exciting time to be a pavement engineer. It will change. AI will change our field pretty soon, but the entire world will be changed. So we should embrace it. Just before I conclude, I would like to thank again the International Road Research Alliance and MnDOT for giving me the opportunity to give this lecture. And I would like to thank sponsors of this research and many collaborators for the project. And I will be happy to answer any questions you might have. Thank you.
All right, we're going to move on now with our program, starting with the first session, and it's going to kind of remain in the concrete pavement world. And what this is going to be about is research results related to sustainability, concrete pavement sustainability. We're going to be having 5 presentations. The first one will be Dr. Peter Taylor, who is the director of the National Concrete Pavement Technology Center, also a research professor in the Department of Civil Construction and Environmental Engineering at Iowa State University. He helps agencies and contractors implement best practices in concrete pavement design, construction, and maintenance. His research is focused on developing sustainable mixtures engineered to meet the requirements of the environment that'll be used in, and developing test methods to prove that a mixture on site is going to survive. He is a professional engineer registered in Illinois and active in multiple professional societies. And today he's going to be giving you some highlights of the lessons learned from trial batching, construction observations, and early laboratory results related to the sustainable concrete pavement sections that we've constructed in the last 2 years. Please welcome Peter. We're working on getting his presentation going here.
All right, thanks very much, Tom and Ben. I actually have to agree with Lev about the language. When I was in high school, there was a bumper sticker floating around saying, "Keep death off the roads, drive on the pavement." And what it meant was drive on what you would call the sidewalk. So yeah, when I first met Shiraz Tayyabji and he kept talking about pavements, it was pretty confusing until I figured out the difference in terminology. So yeah, us foreigners have a hard time sometimes. All right, talking about the 24 test sections, a very quick start to what we did, why we did it, and how it's going so far. Then will be more detailed presentations by other researchers based on the reviews that we've been doing over the last couple of years. So that's not working. A lot of kudos goes to Minnesota DOT, to NRRA for opening up the test sections at MnROAD. I think Glenn is probably responsible for a large part of that decision, and Maria. And, you know, the questions that were trying to be addressed with those sections that we built were, why should we build these things? Well, what I'm going to be talking about is why we built it, what we did, and how it's going. And you all know where the section is, so we don't need the image. Why build it? Well, federal highway, state agencies, and indeed the cement industry or the cementitious materials industry is working hard to reduce costs. Although the cement industry would still tell me, we don't care what the feds are doing, we're going to be at carbon neutral at 2050, so talk about it at will. So my presentation today is not funded by feds, I can talk about carbon. But you know, the impetus when we were doing this work was very much to reduce carbon impact from cementitious materials in our pavement construction. And as Lev said, this is a real exciting time to be a pavement engineer, because not only are the design procedures changing and getting better, but the materials are changing. And some of you would say not getting better. But yeah, we have a whole swath of different materials available to us, which means we have to work hard at understanding them, how they perform, and how to work with them, which is a fairly large part of this conversation. And there are a number of innovative people out there developing interesting and new combinations of current materials and new materials. And, you know, as conservative engineers and control freaks, and most especially DOT-based, very conservative control freaks, we're very reluctant for change. And so an opportunity like this to actually build something and see how it goes is huge. So the questions we are trying to ask: can we build with them? Is it possible to get it on the ground? Do they work? And how long are they going to last? Those are the fundamentals that we always ask when we're doing design and construction of any system. So 24 sections have been opened up. First of all, we did 16 sections in 2022 and another 8 in the concrete world last year. And initially, Maria set up a committee. I can't remember, Maria, I think you called it the super committee or something. Super tap, there we go. It was a group of us that got together and said, how on earth are we going to put some boundaries on this thing? And the thought process was, okay, we've got cells, we're going to be about 250 feet long. Structural design is going to be the same on all of them, so that wasn't going to be a variable. It had to be able to be batched in a ready mix plant. We weren't going to permit any fancy construction systems. It had to be run through a slip-form paver by an ordinary contractor. And for quality, we opted to enforce the AASHTO R101 performance engineered mixtures metrics as appropriate, acknowledging that in some cases, some systems wouldn't need air, so we wouldn't enforce the air void system parameter. In some cases, the chemistry is completely different, therefore the resistivity number may want to be a little bit adjusted because of the chemistry of the system. We did insist that trial batches were produced, and many of them did comply with that. We also asked all of the manufacturers for environmental product declarations. I'm not sure we've received all of those yet. So the standard design, 270 feet long, 29 feet wide, 7.5 inches thick, with the same foundation system. And they're all about the same. Now, one of the things that came up is that when people started hearing about it, the control of the program, the super tap was functionally shut down, and the DOT hired consultants, mainly led by Larry Sutter, to become the front face of the communication, the decision-making, the planning, and he earned every penny of the money that he was paid to keep some sort of control on this thing. And a lot of people started phoning Larry saying, I've got the perfect gray powder. And Larry would say, cool, I need 50 tons. Oh, I can give you a cupful. Yeah, no, we're building a pavement here. And so that sidelined a lot of people. But eventually we did manage to proceed with getting some stuff on the ground. So a very quick run through the plan, a control panel, the standard Minnesota mix. I started to jump up and down and wave my arms around and say, you can do better with just existing mixed proportioning. So they listened to me and rolled their eyes and said, yes, Peter, sure, fine. We'll do what you say. Shut up and go away. And so we did a mixture where I took the same materials. I just rearranged the proportions of the aggregates, and I cut 70 pounds out of the cement content. The final spreadsheet made it 501 pounds, and Tom Van Dam has great delight in mocking me about that pound, but that was an Excel rounding error, so I'll stand my ground. And the idea being on that optimized one was that, again, if we get the aggregate proportions optimized, whatever that means, we don't have as much space between the aggregate particles to fill up with paste. So we can cut back on our cementitious system. And again, if we get it right, we don't lose any of the other properties. The workability is still good, and in fact, and sometimes better, while the water cement ratio controls the performance. And so we're getting all of the performance that we're looking for. All right. Then we had 7 nominally different supplementary cementing materials, and the list is there, and I'm not going to read it. We've also put up there just the numbers of the pounds per cubic yard of binder in each case. And again, these companies were able to produce sufficient material to be useful on this site and to get it to the batch plant. There were 3 alternative cements, an ash grove calcine clay with 30% clay. There was a 20% limestone, and that was that request from us, because the thought was, if we're getting 15%, hey, we're engineers, 15% is good, 20% is better, right? And Continental agreed to provide us with that material. And then Ultra High was a non-Portland cement proprietary product. And then there were 4 other cells, which I was involved in, with carbon injection. The theory being is that if you inject frozen CO2 into the ready mix truck at the time of batching, that CO2 would mineralize and help with the hardened properties of the mixture. The catch being, and their claim was that you could cut the cement content back because you were getting the better performance out of the mixtures. And so we had a standard Minnesota DOT mixture with and without carbon, and then the optimized mixture with and without carbon. The one thing that did happen in this case is that the suppliers were a little bit nervous. They were told, have at it. If it fails, it doesn't matter too much. Do your best. But they were kind of nervous. They were worried about the high visibility of this, and they didn't optimize as much as they possibly could. And they also subsequently learned that with the Portland limestone cement as the base material, they actually needed to put in a whole lot more carbon to get the performance. So not a whole lot of difference there. You can see the binder contents there, and he pulled out about 20 pounds of binder. So not a loud signal coming out of the one, because it wasn't very different. So the control and in 2024, we were given another 8 cells. 2 of them, we had the control again, 2 cells with microspheres instead of air bubbles. And this one I'm really excited about, is that controlling air is a real nightmare. And so if we could throw a powder in instead, quality control comes a lot easier, reliability becomes a whole lot easier. And so the manufacturer donated enough material. And again, we did a standard mixture and an optimized mixture. And Tara will be doing a whole lot more discussion about this one tomorrow. This time we also got an LC3 cement. This is 50% clinker, 30%, 35% limestone, and clay, and 15% limestone. And this product has been around in Europe for a while and is getting a fair amount of traction here in the USA. And then 4 other products, which are basically different combinations of materials we have available. Some of them with a secret sauce to make them go faster, but in general, it's combinations of slag, fly ash, Portland cement, clinker. So those are the 24 cells. We were out there I was there for most of the cells in 2022. A couple of my staff were out there last year. And, you know, basically we kept a conversation going with the finishing crew. And if they were sweaty and grumpy and angry, that was bad. If they were not complaining too much, that was good. And so it is a critical part of a pavement construction, is that if the material is hard to get down and the crew has to fight with it, you're probably damaging it in the process of fighting with it. And so we were tracking how it went down. We also had a whole bunch of tests happening. Is that every fifth truck or so that was arriving on the site was pulled to one side at a speed trap and unloaded a couple of yards of material, and a whole plethora of samples were extracted, both by the AET team and by the Federal Highways trailer. Both lab facilities were pulling samples. And so we measured hardened properties, durability properties. We were trying to look at carbon, and again, we were looking for EPDs. The way that it's been reported so far and the documents that have come out so far has basically been looking at cement content or clinker content has been the measure that we've been able to apply so far. All right, then, is Bernard here? Yes. Oh, there he is. This is Bernard's baby. If you got any questions about this image, he had a lot of fun putting down a whole pile of sensors, and is still having fun reading the data coming out of these things. We were trying to measure everything that we could possibly measure. And then every year, going back and having a look at what are we seeing? How is it standing up? Is it spalling? Is it cracking? Is it raveling? Is there any other distress? And so we're now we were up there here, a month ago, did a quick look at some of the sections or all of the sections to see how they're doing. And we will be reporting those in detail a little later. So a couple of the key things that we learned. Many of the suppliers delivered the product in super sacks. And what we discovered is that many of these products don't get out of super sacks too well. Larry and a couple of the DOT staff spent a couple of late nights with vibrators and hammers trying to get the super sacks drained into a cement truck, which then was used to blow the material into the hoppers for the batch plant to be able to put it in place. And I think there was a lot of interesting language late at night trying to get these materials out of the sacks. The other things that Larry talks about, and I've heard Maria present, by the way, a lot of this material I stole from Larry and Maria, so they're not my original slides, is that uniformity. At least one of them, when the manufacturer put the product into the sack, they didn't mix it. So it had a layer of this and a layer of that and a third layer of something else. And so there was very little uniformity of that material, even by the time it found its way to the construction site. And that is a concern. And a message went back to those suppliers saying, yeah, you got to do your mixing before you deliver it. All right. Some of them went down real well. Some of them didn't. One of them had to be lifted up almost immediately because, I'll let Alf and Maria talk about the why part of that a little later. But, it was a case of, it seemed to me that the admixture demand was pretty high. The delivery time was a little slow, and the admixtures had died by the time it got there. And so, some of them were a struggle. But again, this is a learning opportunity. We learned a lot. Slump loss is different for some of these materials. If you're used to losing a slump every hour, you may get more, you may get less, often less. Response to admixtures is different. Adding a couple of gallons here and there will have a very different response for these different materials. And the other part of it is response to vibration is different. And this is a whole new world that we're starting to learn to study in a little bit more detail, is that the slump test has been the go-to test of workability since before any of us were born. And it doesn't tell us the information we need, because the concrete finding its way through a paving machine isn't just sitting under gravity, it's getting beaten up by vibrators. And so what we have to understand is, how does a mixture respond when a vibrator is put into it? And I know Lev's group with Julie is working on this. I've got a research project going on it. Tyler Lay is working on it, and we're all happily competing with each other. One of the tests we did run was the V. Kelly, which is built off an old California test, where put a hemisphere on top of the concrete, a 6-inch hemisphere on top of the concrete, and run a vibrator and measure how quickly that thing sinks. And we found a really good correlation between what that device was telling us at the speed trap was reflected very well in what was coming out the back of the paver. And it was even better than the good eyes, you know, because a lot of us standing in front of the paver, watching the material coming out of the truck and going, that looks good or not. And I was fooled at least twice. And in both occasions, the V. Kelly test did pick it up. So I think this one does have some potential to be useful, particularly in the lab and potentially in the field going forward for feedback to the batch plant. Other innovative test that we were running out there was the Phoenix. This is Tyler Lay's test. It's basically a muffle furnace. You take half a cylinder, throw it into a tray, and cook it at high temperature for 15 minutes and measure the moisture loss, and so back calculate the water content of the mixture, which is critical because that defines the performance of the concrete in almost every respect. And the data were internally consistent. So yeah, it's looking pretty promising. And I know the DOT is looking at, I think you bought several of these toys already and using it in the field to replace the microwave. Our university has just landed a contract with Wisconsin to do some review on the Phoenix as well. So how's it going? Well, the strength requirement was 3,500 PSI compression. Most of them made it at 28 days. Everybody made it at 56 days. Resistivity, I don't think we actually imposed a limit, but we asked people to report it. And again, for me, a good number is 20 kiloohm centimeters. We all got there at 56 days. Freeze thaw, that's been more mixed. Some systems, particularly in the 2024 system sections, failed miserably. And the microspheres didn't. So Tara's going, woohoo. Why they failed, don't know. Doug Hooton saw the plots, and his response was, yeah, these systems are not mature at 14 days when we started the test. Maybe we should be thinking about running that test at a greater age. So we're talking about that right at the moment. Some grinding was needed for texture. I think part of that was because delivery, particularly in 2022, was a little slow. And I think some of these systems actually were setting up by the time they found the way out the back of the paver. And so getting texture on them was hard, and they had to be ground to get skid resistance onto them. Otherwise, basically what we're seeing is a little bit of minor spalling, a little bit of cracking, a bit of FOD. FAA would be excited, but we're not. And all of them seem to have survived at least 3 winters so far. So in general, how's it going? Pretty good. So to me, the hard part has been the delivery and the construction part. The survivability seems to be okay so far. So some systems are a little closer to being ready for prime time than others. Trial batches and trial placements are critical. There was one difference between the 24 and the 2022 work, is that it was insisted the day before they had to make a truck and dump it on the ground, and you were putting it out as a stripe. It wasn't coming through a paver, but having a look at how it's looking as it comes out the back of the truck so that we could get the batches correct for the ready mix plant, not just labcrete. And I think that made a pretty big difference in making it more user-friendly. Water control is absolutely critical, and more critical than it ever has been for traditional materials. Fresh behaviors are all over the place. So again, the rules of thumb for our finishing crews are now no longer valid. And we're working actively to figure out what tools can we provide to the finishing crews to help them do their jobs a little bit better. Hardened properties seem to be generally okay. Durability so far seems to be pretty good. And if anybody wants to go, you got a trip to go, an opportunity to go to MnROAD tomorrow. I'm assuming there's going to be a red carpet for at least for Lev. Okay. All right. So I guess the key message from all of this, same old, ain't the same. Life is going to be different. It's an exciting time to be a paving engineer. And with that, I'm done. Any questions? Anybody want to argue? Did I say anything stupid? Right. Oh, thank you.
I was just gonna pop in and there's a bunch of people standing in the back. We do have a number of seats up here towards the front, a whole table on the side here, and some sort of in the middle. So if you want to come sit down, you're welcome to. Got plenty of room.
Why don't you pull it up? Okay, I'm going to have Derek pull up his presentation here while we're waiting. So the next presentation is going to be 3 very rapid 10-minute updates. Peter gave a very good introduction of the cells that are going to be talked about. These guys are going to talk about, including Peter, what are they seeing in the cells, looking at them closer. First presenter will be Derek Tompkins, and he is a senior engineer at APTech with over 20 years of experience in pavement engineering testing, research and consulting. His experience includes leadership and key roles on state, municipal, and federal funded projects. As a private consultant, he has assisted owners, developers, and contractors on airfield and highway payments and low-volume road engineering. Please welcome Derek.
So I am stepping in today for Prashant Ram, who is the principal investigator on this study. Prashant is a sustainability and concrete pavements engineer with Applied Pavement Technology. Okay. Can everyone hear me? And this is the extent of the team. As Dr. Taylor mentioned, Larry Sutter's got his fingers in all of these. So Larry Ton Van Dam is also included as a consultant. And then this is Nichols and APTech collaborating on this project. And these are our TAB members to the right. Again, I don't have a lot of time, so I'm going to buzz. Prashant gave me a load of slides, and I'm going to get to the part that I've participated in. Prashant was unable to come today. So what I have done for this project is perform some of the evaluations of the pavements as I would for airfield and highway pavement evaluations. So I've kind of come out to MnROAD in part because of my proximity, but also because of my experience and taking a look at these pavements as kind of a neutral observer, not knowing much about the mixed designs themselves. So we are currently talking today about the second year review. However, we've just in March performed the third year review. We had to move that up 6 months due to MnROAD construction cycles. So we've now performed all 3 surveys that are required under this contract. And there'll be a report coming out soon on the survey that was performed in March 2025. So I'm here to talk to you today really briefly about these cells, which Dr. Taylor had reviewed briefly, and which I'm not going to talk about too much. You have the information, and he went over what these mixtures are. They all have different kinds of alternative cements in them. There's the blended cement with calcined clays. That's the ash grove. The Terra CO2 is kind of like a manufactured fly ash. The control is a little bit different for MnDOT, or at least now it's the new standard, which is that it has the type IL in it. And then the Continental, the CC is a slightly higher fraction of the PLC. So here's just what I'm here to talk about really quickly, and Nick will be doing the same from Nichols for his sections in there. Is really the only recurring distress that we saw, had nothing to do with the paving mixtures. This was due to a construction issue, and that's now being attributed to a roller finishing an asphalt shoulder, kind of riding up on the edge and creating this kind of regular distress in the driving lane at regular intervals. Other than that, as Peter said, they look great. They look like highway pavements. We don't really see anything that could be tied back to the mix itself, the paving mixture. Some things can be mostly tied to the joints, the transverse joints, and incompressible material getting into those transverse joints, and then the panels moving as they do. And so we're seeing some minor spalling. We're seeing deterioration of corners where the transverse and longitudinal joints meet. Otherwise, there's really no significant structural distress in these cells. So now I'm going to buzz through. This is the cell that was pulled. This was the ultra high materials cell. It was there for year one only. There was 15 feet of it. That photo is exactly what it was. That was what had survived construction. Basically, all it showed us was that it kind of gave us, if you in the lower right-hand corner, we saw a lot of ragged saw cuts near it. So it's kind of demonstrating that timing is really important, that people were unfamiliar with these mixtures. And that's something that we'll need to keep an eye on as we transition to alternative products, is that we need to re-educate ourselves on how these materials behave once they're placed. This is the cell 2214 that has had the largest loss in overall condition and ride quality. Really, again, we saw some local pop-outs here, but otherwise we're seeing the spalling behavior and a little bit of corner damage that we're seeing elsewhere. We are also seeing, again, the majority of these cells were significantly diamond ground, meaning that the majority of this were taken. I don't know how much they ground, but there are areas that show that there may have been some, surface cracking, likely shrinkage cracking, having to do with paving conditions and timing. And so you'll see a lot of that in the shoulders, because a lot of them are unground. So you can still see that surface cracking in place. But what's encouraging is that a lot of that surface cracking isn't really deteriorating. So it's kind of showing that this is superficial and also just kind of superficial, that this isn't really going to significantly affect the life of the pavement. But there are some areas where the diamond grinding wasn't deep enough to take off the shrinkage cracking, and we can see some deterioration of that shrinkage cracking. As Peter said, these are highway pavements. These are not airfields, so we're not worried about FOD generation. So we're pretty okay. And this on the lower left right here, this is an example of in driving lane, kind of superficial, the shrinkage cracking that's happening, where we have seen some deterioration. You can see a little bit of voids developing around that. But again, beyond the progression of that, the slight widening of the cracks, it's nothing that's affecting the performance of this cell. And this is the Terra CO2 is the manufactured fly ash. I believe the replacement rate was 35%. And again, not a huge loss in condition index, but we're moving from year one to year two. Otherwise, we're seeing deterioration at joints and corners of joints, as we do in all cells. And here's the continental cement. Again, very similar. There was a patch in this cell that was performed when a panel was replaced, and you can see that we still see some deterioration around that, having to do with incompressible materials getting in and panel movement. Here's the control. And again, control is demonstrating a lot of the behaviors we see everywhere else, so it's serving its purpose well. No fatigue or damage that can be tied directly to the paving mixtures. Instead, the control is a really good control in this study because it's demonstrating that the presence of surface debris matters, and that as these incompressible materials get into joints, you can have damage that's associated with that. The control section is near kind of a turn-in to the main line. I don't know if you know the MnROAD sections well. There's kind of a turn area, and the control is the section that kind of is right on top of that. So it sees a lot of surface debris, and as a result, we've highlighted areas where we see the kind of minor spalls that develop from the presence of incompressibles and joint movement or panel movement. So that's it. This is the monitoring and summary. Overall, we see that the pavements were performing well. They're performing as expected, and nothing that we see in the condition or the stress can be directly attributed to anything to do with the paving mixture itself and the use of alternative products. And then I have some really quick, with apologies, here's a figure of the loss of condition or effective not loss of condition. We got roughness. Again, the roughest cell was the 2214, which was the Ash Grove, but it's tough. I added a note that, because it's tough to gauge smoothness on really short test sections. Surface friction numbers were performed on unground areas of the pavement. So these are not really a true representation of the friction out there because most of them are diamond ground. LTE looks fine, no real change there. And then finally, the year 3 survey was performed in March. There'll be analysis and reporting to follow. And then there's an evaluation of the sustainability practices. This is where Prashant really knows his stuff. And he's also been complaining about no EPDs, and he's waiting on EPDs. So that'll be something that's important for the future work. And that's it. Oh, thank you very much. There we go.
All right, our next presenter, Nick Weitzel. I'm just walking up here. All right. Presentation, what is that? All right, Nick Weitzel is a senior engineer with Nichols Consulting Engineer with over 9 years of experience, holds an MS in civil engineering from the University of Nevada, Reno, and is a registered professional engineer in California, Illinois, Nevada, and Tennessee. He specializes in pavement evaluation projects using a variety of destructive and non-destructive testing, and is a leader in traffic speed deflectometer data analysis. He's going to be covering the alternative pozzolanic materials.
Thank you, Tom. You guys hear me in the back? Okay, let's get going. So this is our second year performance update. As Peter said, these sections were built about 2.5 years ago, August of 2022. And I'm talking about the alternative pozzolanic sections. So 16 sections in total were built. 5 of them we just heard about Derek, Vrtis, APTech. Peter's going to talk about another 5, which had the carbon sequestration and carbon mineralization. But I'm going to be talking about the alternative ones. There's 5 sections with the alternative, and then we also had the optimized Peter's baby. If anyone has not seen this, they're on the main line. And so these sections are actively getting trafficked right now, even getting a pretty significant amount. Project objectives, you can read all of them here as we have in our scope, but really it boils down to 2 questions. Do we want to keep using these materials? And if that's the case, how do we ensure that in the future we get sufficiently good performance? Here are the tasks, as Derek showed, talking about the second year update. And these are the materials. And so starting up at the top, we have the standard paving makes for MnDOT, 570 pounds of cementitious, 30% fly ash, which is 140 pounds per cubic yard. And as we go through, starting at the top, we have best pumice and natural pozzolan, that was added at 30%. We have the OptiPoz, which is a metakaolin, so a calcined clay, that was added at 12%, and then 18% fly ash in that mixture. We have a 3M natural pozzolan, which is here used in Minnesota and has been, I think, for a few years now. Granulated roof shingles, which is added at 12% or 15%, excuse me, and then another 15% fly ash. We have a ground glass pozzolan from Urban Mining called Positive, and that was added at 30%. And lastly, we have Carbon Limit, which is a 3-part proprietary blend that I believe only Larry Sutter has been given the details, and I'm not sure he can share them without being shot. hopefully we'll get that. I think we will. Again, added at 30%. This is the one that, as Peter mentioned, was delivered in layers. And so you can still see it in the pavement surface, how those materials still do not blend up to where the supplier wanted them to be. But that's the devil with the super sacks. And then lastly, the optimized gradation, which is all the same materials as our control mix, just slightly different aggregate blend. We have a couple of different graphs here. As you can see with the joints falling, a lot of it was low severity, and it was relatively consistent among all the test sections, not just for these alternative pozzolan ones, but for all 15 of them that are out there. Trying to group together kind of the area distresses, scaling, mat cracking. Only a couple of the sections really had any noteworthy distresses that are out there. Generally, they're performing pretty well, but let's get into each of the sections. With the urban mining, the positive, this one looks pretty good. I know it's hard to see with some of the pictures in the back. Generally, it looks pretty good. You have a little bit of finishing issues on top in certain spots, areas where the workability wasn't great. Finishers had to add a little bit of concrete to get everything nice and smooth, but overall, this one's doing pretty well. We get into the optimized. There was one area where it was a little bit dry. You can see it was a hard time trying to get this to consolidate over the winters. This has started to blow up a little bit. But by and large, this spot in particular has not continued to deteriorate, which shows that this was just kind of an isolated incident, most likely during construction. With OptiPods, it's always hard to try to show this in pictures, but on the left, you can almost imagine as someone came in with their hand and kind of dragged into the surface. There's a few of these streaks that have given up material. But again, these also have not deteriorated, which makes me think that this was just a dry area. It flaked up after the first couple winters, and once we got back down into the solid material, things are performing pretty well. On the right, we do have a lot of scaling in this section as well, as you had saw in the graph. When we get to the 3M section, this one actually looks pretty good. You wouldn't think that this was 12% granulated roof shingles. We had a nice smooth texture, doing pretty good. Hess pumice is the only section that we had that actually had any sort of cracking in it. Here we have a longitudinal crack that goes through 2.5 slabs. From what I remember a month ago, this crack has grown a little bit in length, but severity-wise is still holding together. And carbon limit. Carbon limit, again, being the one that was our 3-part that was delivered unblended. So I'm sure that there is some impact of that with these areas. It was relatively dry mixture. You can see that in the image here to the right, and again, a little bit on the right side of the image on the left. Very dry mix, very hard for the finishers to try to get this consolidated and get it smooth. A lot of water added. After the first winter, you can see MnDOT added some bituminous patch material to these areas, tried to get it to close up, but they deteriorated a little bit more. And eventually these 2 slabs on the right became these 2 slabs up here that were replaced. The replacements are doing very well, by the way. That was the ugly, but overall, I know these pictures are small. The sections do look good. Things look pretty good out there, considering that we've been through 3 winters now. So where do things stand? I'll let you read the image on the right. I hope anyone from Indiana DOT is not offended by this. I did not make this. This was an image I found, the only image I could find on Google, the only meme I could find about pavements. These are new materials, right? A lot of these materials have never been through a batch plant. They've never been through a paver. A lot of these material suppliers have no idea the needs of the concrete industry, what we're looking for in terms of workability, material properties. There's a lot of learning that needs to be performed with these. And with only one placement, by the time the finishers get this through the paver, I guarantee you after about an hour after construction, the paver operator knew changes, the batch plant knew what changes makes designers knew what we needed to do. You know, with using these materials more, we will gain this experience, and a lot of the issues that we see on these sections will be eliminated. So to bring this full circle, where do things stand? Do we want to use these? Yes. You know, and I know that we say that, you know, the carbon benefits of using this are tremendous, but I'm from Nevada, and you can get fly ash, but it's extremely expensive in our market. And so from my standpoint, there is no going back. We can't really use fly ash. We need to start using some of these other natural pozzolans. Anyone that knows anything about economics knows that as demand goes up, price goes up. And that's what we're seeing in our market. Trying to let these new materials in is going to help lower the cost. Our second answer, how do we incorporate this? Well, we haven't really dug too far into that right now. Again, trying to come into this not being too quick to say that this works or this doesn't work. In fact, I saw a plastic pavement go down in California a couple years ago. It went down on a Friday, and that night there was all these news articles about how great it was. And come Monday, the Caltrans decided to mill that sucker out. We can't be too quick to judge these materials either way. You know, the proof is in the pudding. And after 3 years, it looks like pretty good pudding, but we need to be a little more careful. So again, third year site visit was conducted a month ago. That report's going to be coming out, I think, at the end of this year. I think was it 1 year and 8 days? Not that I'm counting days, but our final report will be due, and shortly thereafter it will be publicly available. I know that some of our other reports are already up on the MnDOT website, but here's my email if you have any other questions. Thank you.
All right, thank you, Nick. And actually, to make your life interesting, the executive committee of NRRA has decided to extend your contract, so you'll get to monitor these for a couple more years. So, final presenter for this little section here is Peter Taylor. He's been introduced before, so he's going to be talking about the sections that had the carbon injection.
Hey, thanks, Tom. All right, I'll play through this pretty quickly. As I said earlier, there was 2 sections put in with carbon injection, and the reason we had to have a different set of controls, it was the source of the materials. So the theory, this is a slide stolen from the provider of the carbon injection product, is that carbon dioxide will react with the hydroxide hydration product, and so form a more stable solid. So the thought is that if you inject some CO2 into the mixture very early on, you can promote early hydration and get a better performance out of the system. So we did four panels. I'm going to talk about the 4. The other one, which was carbon upcycling, I guess the message from that one, I didn't put it into this presentation, is much the same as you've heard of all of the others. Done right, the data is looking fine. It's okay. But I did want to focus on this one. The one catch is that when the project went out to bid to the ready-mix operator, they did not have the infrastructure in place to do carbon injection. So for these 4 panels, we used a different ready-mix operator. And to keep it consistent, we needed the controls because they used a different Portland cement as their base material. And I think they even used slightly different aggregate combinations. So we had an optimized binder and the conventional mixture, 2212 and 2217, and then the same 2 mixtures with the carbon injection applied. As I said earlier, the optimization was pretty limited, and it's ain't got a mouse. But you can see the optimized has only been dropped by about 20 pounds, which is not an awful lot. And in fact, I'd be surprised if you saw any signal from that. The other thing to note, Bernard has been harassing me pretty hard. Can we measure the carbon dioxide that's been injected? You know, because the trick question that all of us were asking is, it gets blown into the truck, how much of it evaporates out almost immediately? And nobody knows. And so the thought process is that could we measure the CO2 in the hardened concrete? And we've run some TGA and not found any convincing data. We've been in touch with the really smart people at NIST who can measure anything. And they've come back and shrugged their shoulders and said, no. And it's not entirely surprising is that the amount of CO2 that is 6 ounces, not 6 pounds. So when you're putting 6 ounces into 4,000 pounds of material, are you going to be able to measure it? Yeah, that's too many significant figures. And I spend my life harassing students to not put 18 significant figures into their data. So it's not entirely surprising. We can't see it. Let's move on. So, you know, like all the other panels, we were watching how they went down. The Minnesota mix with the carbon injection went down beautifully. The crew loved that one. On the right is the optimized mix without the carbon injection. That was a little crunchy. Had to have a little work to get it finished. That was probably the worst of the 4, and this was the best of the 4. The other 2 were somewhere in between, mostly just fine. So again, I don't think that we're seeing an effect of the carbon injection on the workability of the mixture. Lab results, again, this is resistivity. The red lines are the Minnesota mix, the green lines are the optimized mix, and the dotted lines are the with the carbon injection. And yeah, not a lot. Oh, sorry, the solid lines are with the carbon injection. Again, not a lot of noise, not a lot of variability, not entirely surprising. And the same plots exist for the compressive strength, the flexural strength, the modulus of elasticity, just about everything we measured. After 2 years, we did do distress mapping and droning. The other speakers have already talked about this, and all of the panels exhibited a little bit of spalling. Load transfer, there was more noise coming out of whether it was on the traffic lane, the heavy lane, or the high-speed lane. Very little signal coming from the differences between the different mixtures. All of them seem to be doing all right in terms of ride quality. And again, all the signals we're seeing are not related to the differences in the mixtures. Again, no clear signal from faulting. Friction, we're well above action limits, so they're doing fine. Dynamic loading, all seem to respond in much the same way to vehicles going over them. So again, the signal coming out of this is, yeah, it's fine, carry on. That's after 2 years. As the other speakers have said, we were up there a month ago, did a whole bunch more work. I got this file yesterday from the student, and I didn't look at it before coming this morning. I apologize. So again, the last signal, the information from this in summary is the carbon injection doesn't seem to have hurt. It doesn't seem to have benefited a whole hell of a lot, but at least it hasn't harmed us. Carry on if you wish to. And with that, I'll hand it back to Tom. So thank you.
All right, we're going to switch gears a little bit, and in the theme of sustainability, one of them is pavement preservation. So Mike Wallace here is going to be talking about our efforts in tracking some preservation techniques that we've been experimenting with out at MnROAD and some other sites. Mike Wallace is a research scientist with the Office of Materials and Road Research and MnDOT here and has been with them for about 6 years. He's heavily involved in the areas of concrete pavement, instrumentation, and the use and implementation of innovative equipment and techniques for measuring pavement condition and response. So please welcome Mike.
Thanks, Tom. And Tom's actually the PI on this one, so thanks to him for all the work he's done so far. So yeah, talking about preservation techniques of concrete overlays. So concrete overlays, they're typically 4, 5, 6-inch thick concrete layers that are put on an existing pavement, bonded to asphalt or unbonded to another layer of concrete. And we're trying to extend the life of these pavements, typically looking to get another 15 to 20 years out of them. And what we're seeing is that's not quite the case with them. So one of the things we've been trying to do is seeing if diamond grinding can buy us a little more time. What we're seeing is they're faulting after about 8 to 10 years. So if we come through and grind the surface smooth, will that buy us another 5 to 10 years? And we were really looking at 3 different locations. We had the 4 MnROAD test cells in 2022. And then over in Washington County, we had Valley Creek Road. And then there was another section in North Branch on I-35. And then kind of another side study that we were looking at was determining if we could use PEM materials to put into some of these repair panels to see if that could extend the life as well. So the PEM materials was only used at the 6 MnROAD test sections. So right now we're at task 5, which is for the MnROAD cells mostly, is the 2nd year performance report. And we've been collecting a lot of data. We have distress surveys and then FWD, fault meter, and fault meter is kind of the big one we're looking at. And then also ride quality measurements. So for the Valley Creek Road, it's 5 inches thick over a 4-inch asphalt, and that asphalt is 42 years old. So kind of asking a lot out of it. And they put 6 by 6 foot panels over it in 2012, and it didn't really last as long as they were hoping for. And in 2021, they were kind of looking to see what they could do. The faulting at that time was an average of 2.2 millimeters, which once you start getting over 2, you're really going to feel it. And also had values all the way up to 4.5. So really starting to get a rough ride there, and they wanted to figure out what could they do to extend the life of that road. So overall, this is just a picture after 2 years. You can see the panels themselves were actually in pretty good condition. So this is after 3 years of diamond grinding. And then this is just kind of showing there was 13% of the panels were cracked, but they weren't really too severe of cracks, and just kind of showing some of the progressions over the years. And then here's some more photos. I think this was kind of the most severe crack that we noticed, but overall just in good condition besides the faulting. And now looking at that faulting, this is a lot of data all on one slide. This shows our pre-grind and then years 1, 2, and 3. And that black line there is year 3. And so we were kind of disappointed to see that the data itself was showing that faulting values were returning pretty quickly after 3 years to pre-grind levels. And again, this just kind of shows the comparison of pre-grind faulting to year 3. And you can see they're pretty close to what they were before it was ground. And then looking at the IRI, pre-grind values were up around 150 in that driving lane right wheel path. And then after post-grind, they were able to get it very smooth, under 50. But then after years 2 and 3, we were up back towards 100. So overall, the summary of this section, the panels themselves were in good condition and they really weren't deteriorating too quickly, but the faulting values after 3 years were approaching pre-grind values. And the ride quality we saw was approaching, but not quite to pre-grind levels. So then we were also looking at 6 MnROAD test sections, and this was kind of a combination of 4-inch thick and 5-inch thick concrete overlays, and we had fibers and we had bonded and unbonded. So we had a whole variety of different sections that we were looking at, and we diamond ground 4 of those sections, and then 2 of them we left alone. And they were also exhibiting quite a bit of faulting. So it was a really good opportunity to see if diamond grinding would help buy us a little more time in those sections. And one of the things in these sections is a lot of the panels were cracked and required repairs. So we were testing out a different type of repair where we were using tie bars and then a PEM mix, which was actually the same optimized mix that Peter talked about in his study. And we were using it in these panels to see if we could extend those and get it to work. So just to kind of compare from we did see that there were some issues with those repairs, but we wanted to confirm that it wasn't a mix issue. So this just kind of shows the strength results between the control and the optimized mix. Really just shows that the mix itself wasn't the problem. And a big emphasis here is these MnROAD test sections experience a lot of traffic, much more than your typical 4 or 5-inch concrete overlay is ever really going to experience. So a lot of accelerated distress is going to happen from this. Now, starting out with section 160, really wasn't in horrible condition, say about moderate distresses. We did replace a handful of panels there, and this just kind of shows the picture of what it was looking like after 2 years. Really not too bad. And then this is just a couple more pictures of the severe cracks that we saw. But the big question is faulting. So this shows the progression of faulting from 2013 when this panel was originally installed. And you can see the pre-grind values average was approaching 4 millimeters. And then post-grind, we were able to get it pretty smooth. But then after 2 years, it really came back pretty quickly. So. And then again, with the ride quality pre-grind values, we were able to, or pre-grind, it was in the driving lane right wheel path, we saw 133. Got it pretty smooth after grinding, but then after years 1 and 2, it came back very quickly. So overall, the distress levels wasn't too terrible for this. Number of panels were increased, but the big question is the faulting. So the overall faulting came back to pre-grind values after 2 years. And I will say all these MnROAD test sections were removed and replaced in 2024, so they no longer exist. And then 162, this one was a 4-inch concrete overlay on asphalt, and we were really asking a lot here. This one had a lot of severe cracking in it, and we replaced a lot of those panels initially, and then had to do a bunch of asphalt repairs in the driving and passing lanes here. Just here's some pictures of that. So it kind of turned out to look like a checkerboard eventually. And then here's the faulting. So similar to 160, but actually a little bit worse, came back very quickly. And after 2 years, ended up tearing the section out and replacing it. Same thing with ride quality. And actually this one, the entire driving lane was removed and replaced. So that's why you can only see data after about a year, but deteriorated really quickly. So overall, distresses for this one was high. A lot of cracked panels and faulting returned fairly quickly to pre-grind values. So then section 505 was a 5-inch of concrete over concrete. And this one we saw a lot of cracked panels. This is just highlighting some of those replacement panels also cracked pretty severely and pretty quickly. So ended up replacing a lot with asphalt after a couple years. Just some more pictures of that. And faulting. Similarly here, the entire driving lane was replaced. So you can't really see the progression of faulting after the first year there, but it came back pretty quickly. And then same thing for ride quality. So after 2 years, this section, we deemed the distress levels were very high. That entire driving lane was replaced and faulting developed very quickly in both the driving and passing lanes. And then section 605, again, this was a 5-inch thick concrete over concrete. Very similar, a lot of the repair panels ended up cracking and getting repaired with asphalt. This is just kind of highlighting again what that looked like. But the faulting wasn't too bad on this one, even pre-grind and then after we ground it, but it did start to come back. So a little bit more promising, but not what we were hoping for. And then again, you can see ride quality also wasn't great after 2 years. So then again, similar to the other sections, the distress levels for the entire section was moderate to high. Most of the cracked panels developed after a year, but the faulting itself developed a little bit slower than the other sections. And then we had sections 705 and 805, and these two we didn't diamond grind. And this is just a picture. So one of the things we were focusing here was replacing some of the panels in the passing lane. So these sections were passing lane only after the driving lane was entirely replaced. So this just shows the typical condition of what that looked like. And then shortly after, those panels also cracked. So again, wondering what caused that, or was it the mix? We don't think so. Was it the design of the repair? But then also we were tracking faulting in those repair panels. So we saw that faulting came back quite considerably. So although the distress in the passing lane was deemed low, the panels themselves did crack and deteriorate pretty quickly and to a severe level. So the joints and they developed moderate faulting even with that tie bar configuration. So then again in 805, this was similar 5-inch thick concrete over concrete. And this just shows some of those distressed joints that were replaced in the passing lane. And again, they developed cracking as well. And faulting quite severely, as you can see here. I'm just kind of highlighting some of the extreme values. So with 805, we saw the distress for the overall lane was low, but the panels that were replaced deteriorated and cracked to quite a severe level. And those joints that were replaced developed faulting, even with those tie bars. So similar to 705. So overall from the MnROAD sections, what did we learn? So we saw that the traffic itself is very high. So we have to keep in mind that all of these sections are experiencing accelerated levels of loading, and we're going to expect accelerated distresses here, but the results indicated that faulting will return quicker than we were hoping for. And we also wanted to ask, did the use of tie bars around the perimeter help, or did that lead to critical stresses in those repair panels? And what we saw is they deteriorated pretty quickly. So again, all these sections were removed after 2 years. And then now the final section that we looked at was I-35 and North Branch. So this one was ground in 2023. So we only have 1 year of data from it. And this one also used a similar configuration of tie bars in some of the repair panels. But when we were out there testing this one, we set up a test section that did not include any of these repair panels. So this one was constructed in 2009, and again, similarly was designed to last about 20 years, but after about 10 years had considerable faulting. And this just shows one of those sections where the tie bars were put in. Also, we put in fabric to try and prevent cracks from propagating through. And this is what it looks like in 2024. So overall, most of the panels themselves were in pretty good condition. But the faulting's sort of coming back. So this shows our pre-grind and post-grind values for both the driving or for the northbound and the southbound sections. And after pre-grind, we were able to get it fairly smooth. And then after 1 year, they were starting to tick up, but not too considerably. So we're actually planning to go out and collect fault meter on this section and FWD in about a month. So that'll kind of be our final section or study to see if diamond grinding works or not. So then the ride quality here. Still after 1 year was very smooth, so that was good. Again, just overall, the distresses in this section were very low. Faulting, although it started to come back, it really wasn't anything to be concerned of yet, but we'll see. We're going to continue monitoring this one. So, like I said, the MnROAD sections are gone. We're no longer collecting any data for those, but we've got Valley Creek Road. We're hoping to get another 2 years of data from that. And then I-35, we're hoping to continue for 3-4 more years. So we'll see. Again, just in general, not super happy with what happened for diamond grinding, but yeah, with that, I don't know, do we have time for questions? Yeah. Say that again. Yes, and I went through that really quickly, and we had a 100-slide presentation that we gave to the TAP last Friday, and I tried to cut it down as much as possible, and we're just about to release a task report that's going to go way more in depth, probably in a couple weeks. So, yes. Do you remember grind depth? Was the question?
No, we don't. No. No.
No.
Yeah, just a comment about, when we're grinding something like this, we're taking the surface off. We're not repairing the issue really, which is what's underneath. And it's probably the loss of asphalt or inner layer material underneath there. So again, we're not fixing the cause, we're fixing the symptom. So it's not surprising. It's more just, would it be 5 years before return? Unfortunately, it looks like it's not going to even be 5 years, unfortunately. So, but however, some of our latest measurements on Valley Creek was that between years 2 and 3, there was not a significant jump. So maybe there's a leveling off. But unfortunately, we're already at a level where you're starting to feel it again. So it's not really at this point, what we determine a longer term fix that is it worth the investment of going out there and doing this? I'm not so sure at this point, but maybe we'll be proved wrong and it levels off. Again, the interesting thing is the faulting level the measured faulting is the same or has returned, but the ride is still better than it was. So, you know, again, we want to watch both the faulting number as well as that ride quality. You know, if it keeps it smoother longer, even though it's got some faulting in it, it's still going to be beneficial.
Quick question, you have mentioned what is the stability of the foundation?
Yeah, it'd be better to look at the report, because again, I'm trying to explain all that. I mean, so we did try to. Sometimes there's like very little change pre and post grind, you know, with the faulting or with the FWD results. So again, it's probably best to be looking at the reports that are coming out. Mm-hmm. So the question was, did we look at the repairs or the cracked panels? Okay, the reflection cracking. Okay. Yeah. Actually, and are you referring to the repair panels that we did, or just the overall? We did not see that many reflective cracks, you know, and even on some of the repair panels where there was a transverse crack, it actually developed a longitudinal crack in the repair panel. So that was kind of interesting as well. Mm-hmm. All right, thank you. Just a reminder, if you're on the next session, to get your presentation loaded during the break. So now we're going to be taking our break. Enjoy the break.
All right, good morning. All right, thank you so much to allow me to present today. It's my pleasure to be here. And Tyler gave me a really very long title. I made it short. So thank you for the long title. And I'm going to talk a little bit about some work we have been doing in Michigan. Before we do that one, I just want to briefly introduce some of the general background I have. So first, we are going to briefly go over the rubber modified asphalt project in Michigan, and then the chip seal operations we have done. And then we are going to briefly talk about some work. It's ongoing project with NRRA. So that's funded project. Right now it's still ongoing. So basically the 3 blocks of small information here. And the first one, I want to really share some of the rubber modified asphalt project in Michigan. As you can see in this graph here, there are some projects, you know, in Michigan here. There are a couple of projects in the really north side of that of the state. That is where Michigan Tech is from. So it's pretty far away, but really Minnesota is really really nice place to come. You know, Minneapolis area, this great area is really close to this big city we can travel to. All right, it's very, very nice. And then the rest of the dots basically means the project we have been doing with rubber asphalt materials in state. And we do rubber asphalt chip seal. Of course, we also do some regular chip seal work. As you see on this picture here, this is some work we have done in Michigan, and also some of the work we did for MnDOT in the past. And in 2018, we attempted the first one project in rubber asphalt chip seal in Michigan. This is in county of Kalamazoo. So we actually, in that time, we started to do some kind of chip seal work. Some are conventional work, conventional chip seal with emulsions, and some are hot rubber asphalt, which is not emulsions, so no water at all. So that is some work we have been doing. And briefly going over there, you know, we learned a lot of good lessons. We get some good experience, and later on, we are starting to do a little bit more work. For example, the first time in 2018, what we did was we just blended the rubber. You see the big truck here, and then through the conveyor we just transport the rubber powder to a distributor truck, which has the heating element and agitation units inside. And then, of course, after the viscosity reached to a certain temperature, to a certain of a number, we spray that in the field. And on the right-hand side, this picture basically showing the powder, the rubber powder, go into the system. But that was very first attempt. Over here, you can see in 2021 we improved the process. And so we actually started to spray rubber asphalt on the road. As you can see on the left-hand side of this picture here, you see the road get a lot of cracks. It's pretty much really the road really need to be reconstructed. But of course, due to budget limitations, so basically we decided to do chip seal with hot rubber asphalt. And that is operation. On the right-hand side, you see here is just a spread in the chips. Everything else would be the same as regular, regular chip seal operations. Other than really the difference here is spraying the emulsions or hot rubber asphalt. That's really the differences. And that is 2021. In 2022, we started to use this rubber asphalt chip seal to use that SAM layer, which is stress absorbing membranes interlayer. We had a few projects. One of the noticeable one is in Bay County, in Michigan. So we actually use this really thin layer of a rubber asphalt chip seal here as this interlayer SAM layer, and then on the top, of course, we construct the regular asphalt mixture or rubber modified asphalt mixture. So right now, so it's about a year, almost 3 years past. So the situation is really looking really good because of the SAM layer. So the crack from the old pavements are not really coming up yet after 3 winters. So that is something we really work with Bay County Road Commissions, and then get a lot of support from DOTs as well. So for example, this is one of the picture I took here. You see this is the left-hand side of the pavements, and then we start to spray hot asphalt. You see those, it's not emulsion, all right? It's not emulsion. And second picture starts to spray the chips, and then the third picture here is starting to roll in, just make sure it's compacted. And that's pretty much what the process going. And then of course at the end we placed a layer of asphalt mixture on the top, right? So that's how really we put the SAM layer ready. And of course, after construction, things are looking really good. We have a lot of signs. If you ever drive to that area, you can see here those signs. The project is funded by who, and it's a SAMI control section, rubber section, and all those different signs there. This is in the 7 Mile Road in Bay County. And going through today, this is a project we got funded from NRRA. I really appreciate the support from NRRA. And I also appreciate the support from MnDOT, allow us to use I'm25 in this test route. So we got a really good team to work here. Of course, I mentioned the MnDOT, MnDOT, the NRRA, like MnDOT, we got Tyler here and Rob Green, and a group of really good folks to help work with us. And also we have a Bay County Road Commission. They provide a lot of support to the team. So what's the background of this project? Of course, we know we in Michigan Tech really in 2017 worked on a project funded by NRRA and MnDOT, so on the seal coating performance project. And then later on, we construct a lot of rubber asphalt materials, and as in the chip seal in Michigan, quite some miles. And then the last few years, we also start to use rubber asphalt chip seal instead of using emulsions like CRS2P or CRS2M. We use those things to build rubber asphalt chip seal. So far in Michigan, there are over 300 lane miles of pavement has been installed as in a research project using the rubber asphalt chip seal. So then we find out the using hot rubber asphalt chip seal has some really good potential, and so extend the pavement life That's something because after some years, we can see clearly what the difference look like. And we think like, in the long run, this process probably can reduce premature stripping or extended pavement life. That's something we really would love to continue the work. And for this particular ongoing project, the objectives are twofold here. One is basically demonstrate the use of hot rubber seal coating to reduce the premature stripping and, of course, fix the cracks, extend the pavement surface life. That is the bigger goal. And then we also planned some lab testing and field testing so that we can better understand the advantages of using hot rubber asphalt chip seal. That is our bigger goal. And the next few slides, I'm going to show how really we did the construction, what measurement we took, and what we are going to do next. All right, here is the location where the project is located. You can see here in Michigan, the Bay Area. And this road here, we collect all the traffic data in 2020, 21, 22, 23. And we got all the data here so that you can see the traffic actually is pretty decent traffic. It's not really the heavy like interstate road, but it's one of the major MnDOT route. So there are planned, like 2023, like 8,000 AADT. So this stretch is about 6 or 7 miles long. And what we did was in the project, of course, you can see here, 6.6 miles. So in this project, this is 2-lane roads. So we pretty much have about 4 miles of road have less distress, and there are some 2.6 miles have more distress. So we got all the IRI data, and also we even find out the Pacer rating data. So anyway, with those things, we actually construct this one actually 2 directions. So we are using the rubber asphalt materials, as a chip seal, and then only chip seal. That's what we did here. And so one section is rubber asphalt chip seal. Of course, some other sections we also have emulsions, regular emulsion materials as well. And in some of the cases, we have Fox seal on it, just to make some kind of differences, because we also want to really compare, make sure they are all comparable. A lot of the places in Michigan, they love to use Fox seal, but that's not really absolutely required for this project. Here, I want to show you a few equipment here. You can see here right now, this is a hot rubber asphalt storage truck, because right now for this project, we have a central location to produce the rubber asphalt. It's not like the first year of 2018, we attempted using just one truck to blend everything. That was a little bit tough to do. So this time, because the volume of material is larger, and also we have a few other projects nearby, so we have a central locations to prepare all the rubber asphalt. And now we on the right-hand side, this is a distributed truck. So the purpose of this truck is going to spray the hot rubber asphalt on the roads, almost like a regular distributed truck. But this one, we have a heating unit and agitation unit. Just make sure rubber are not going to glue together. And you can see on the right-hand side, on the left-hand side, and this is a spraying truck. We're going to apply asphalt, hot rubber asphalt on the road. And the other picture is shown on the back. What's that? This, of course, this truck's nozzle openings usually are bigger compared to the regular emulsions, because regular emulsions is pretty much a liquid. The viscosity is very low. But for this type of materials, viscosity usually is pretty high. We usually spray this materials about 400 degrees Fahrenheit to make sure it's going out smoothly. The temperature, of course, is high. And for this project, we also did one of the changes was we are using a coated chips. So that is, it's not absolutely required, but of course, it's very beneficial to do so. So that's the reason we have a plant. We produce a pre-coated aggregates. This pre-coated aggregates, the asphalt content is less than 1%. Usually about 0.75% will be sufficient. It depends on the size of the stones. But for this case, you can see the coated one versus uncoated one. We just partially coated aggregate surface. That's all. So the goal for this one is to allow the aggregate chips glue with the hot rubber nicely. Okay, so that's basically the goal. And then this is picture here showing you how really we spray the asphalt. So this rubber content in the asphalt is pretty high, 25%. That's and we are spraying at about 0.55 gallon per square yard. That's so pretty heavy, heavy compared to regular emulsions. So that's really means there are really good products really apply on the road. You probably, when you see clearly, you see closely, you see all the small cracks also be sealed. So through this process. So of course, after that one, we spray the aggregate chips, depends on the aggregate chip size. For this particular product, we're roughly about 30 pounds per square yards being used. And then of course, it's regular operation now. It's compaction, sweeping. That's regular chip seal operation. And then afterwards, of course, you know, after you apply the Fox seal, and on the right-hand side, you see the project's finished. Okay, only one lane finished, and then the left lane will be finished through the other direction. So that is, in general, what's the product look like. Of course, this is after the both lanes being ready. What's that look like? And I do have a small video here to show if this can go and see what that look like. There should be music, but we don't have here that. The music was very nice, but the room is big, so we can just ignore that. So now you see this is M25. It's about 6.6 mile stretch, and the construction, we have some layouts where we which place we have more chip seal with emulsions, or which one has more of a hot rubber asphalt. This is all the equipment we're using. And of course, the reason we put all the equipment together, we also want to really understand what is the environmental product declaration, EPD, in the entire process. That's just a byproduct we are doing. So this is pre-coating the aggregates. And then, of course, you can see this really, we only just need partially coated the aggregates. We don't need too much asphalt. My first experience was we used 1% as too much. We have to crush the crust off. So rubber content is about 25% by weight of asphalt liquid. So now this fellow is going to start to spray rubber asphalt. A lot of vapors come out because the road is cold. It's not smoke. And then, you know, spread in chips, about 30 pounds per square yard. So now you see a process same like a conventional chip seal or seal coat. So after that's ready, of course, we're going to plan to the roller. I have this posted on LinkedIn, so if I interest, I'll share that one with someone. Their music. So the compaction is ready. The sweeping. Just make sure we get rid of the excessive amount of aggregates. Usually there are not much. This is the same as regular seal coating operations. Like I said, you know, we receive a lot of support from different organizations. Yeah, after you apply the Fox seal, looks pretty dark, but that's, in my opinion, is not absolutely required. So just want to show what the difference look like. The cost-wise, this is way lower than regular like overlay or something. But of course, it's more expensive than emulsions-based chip seal. But this project, we use about 6,500 equivalent tires. And appreciate the support from NRRA, MnDOT, MnDOT, and big county road commissions. That is what the picture of the video look like. Silent video. Oops, how can I go next one? Let's see, next. All right. So also we tested a bunch of things. We also test the pull off. If we want to really see what the pull off performance look like. And after 3 days of construction, and test it, of course, when the pavement temperature about 113 degrees Fahrenheit or so, and we test it, we really want to see if the rubber asphalt chip seal have higher pull off force. Of course, you see it's a little bit higher, 243 versus 230 for conventional one. Of course, the thing is the two temperatures are not exactly the same because we only have one device testing both sides. We have to finish one and go to the other one. The temperature drop a little bit or increase a little bit, on the pavement. And also we tested after 3 months. After 3 months, this one was tested about 4 p.m. The temperature that day was about 77 to 86 degrees. That means 77 is in one site and 86 degree is in another spot. But it's still, you can see the temperature wise, you can still see the hot rubber asphalt, the chip seal has a way higher pull off force. That really means even the temperature higher, their force is still higher. That means really good bondings there. So that's basically something really we are looking forward to see. And if you take a look at the entire construction, we also, after that one, we really appreciate MnDOT support to measure all the IRIs and all those, through the advanced, testing equipment, and I go over that, test a lot of things, and we want to really see what's the information look like, after next year, because then we'll have 2 years of winter. Now you see what's really that look like. So that's ideally, we would love to see more years of performance. So right now, the year one, we test it, we get all the IRI, rotting, surface defects survey data. Those are, I think, it's only year one, so probably the data is not very meaningful, but I still have some data. So, so anyway, we test those data, we have those data, and I have some analyze of data, but of course, don't really read too much about this one. Of course, after the chip seal, all the cracks are gone. So you can see the crack really has been improved a lot, but of course, we don't want to really say too much about it. It's only year one, all right, year one. So we also do a lot of work in the lab. So we also prepared, different lab work, like measure and the different content of rubber materials we use. And like say, construction, eventually we use 25% at different temperatures. We test viscosity, dynamic shear modulus, phase angle. We test the creep compliance, those the document. And also we tested on the chip seal side. We checked the sweep mass loss, surface friction testing, and tensile bond strength or shear bond strength, and all those type of things. I just want to show you a few examples of those testing. Here is one of the bond strength tested on the left-hand side. You can see on the right-hand side is more like a shear bond strength test. So there's no ASTM or AASHTO standard. This is something we have to come up with some ways to do the testing. But the first version of the test was under the support of a local road research board program, with and MnDOT just a few years ago. So we actually developed that test that time. And then right now we improve it a little bit and then do the similar testing. To make sure we really can measure what's the bond strength and also the shear strength at the same time. So that is some of the procedure we have here. And some results I want to really briefly show you here. You can see on the left-hand side, those are pictures showing what's the tensile bond strength testing look like. And I summarized the results on the right-hand side. So after different freeze-thaw cycles, and because really we all worry about freeze-thaw cycles. For example, no freeze-thaw cycles and the conventional emulsions, for example, let's say you get the 250 megapascals strength, and rubber asphalt got maybe 280 megapascal strength. So after freeze-thaw cycles, and after each of the freeze-thaw cycles, the strength actually reduce, right? That's we understand. So there are some kind of declining over there, but eventually you can see overall, so the rubber chip seal have better performance even after a few of the freeze-thaw cycles. But that's something very initial results we showed here, and of course we want to really see what happened, in the further testing, and especially in the field conditions after a few years of freeze-thaw situations. And also we checked something like shear bond strength. This is shear bond strength on the right-hand side. This is summary of the results. So shear bonds, for example, shear bond strength, you can see, initially the hot rubber asphalt, it's pretty high, like 175 or something, and then a conventional chip seal rate is about 125 or so. But really after multiple freeze-thaw cycles, you can see there are still some sort of advantages using hot rubber chip seal, right? This is some of the testing we are planning, are currently still ongoing. But I want to really show you a few slides, what it really look like. So in summary here is the direct tensile, right? That's tensile strength, and we call that one. The other is shear strength. Both get improved in the with the hot rubber materials, right? That's the biggest part we see. And of course, ongoing, we are continue doing our lab work, and also we want to really do more monitoring on the field. So I really appreciate the support from NRRA and MnDOT, MnDOT for the testing, coordination, and there's a lot of finance promised from MnDOT side. So with that, appreciate all the support. Thank you so much.
Any questions for Dr. Yu? Ben has a microphone we can pass around for those that do. All right. My group.
That means I can 100%.
Pass. Thank you, Dr. Yu.
Thank you so much.
Okay, so next up, they're actually going to be a bit out of order today. Dr. Fanyan is going to be moved to a later presentation slot. So we have Dr. Michael Vrtis from MnDOT, and he's going to be presenting on our spray-on Rejuvenator Test Section. So take it away.
All right. Thank you, Tyler, for not reading the pre-prepared full bio that we had. Had a lot of fun putting together my bio last couple of weeks, and I was at the National County Engineer meeting last week in Schaumburg, Illinois, and they read my bio, and at the very end of the bio, it says that I'm a self-proclaimed pavement engineer. And the moderator made a joke, or I'm a self-proclaimed pavement nerd, and he made a joke. He said, "Is there a club for that?" And I said, "No, it's a therapy group." So I'm really relieved to be here. Like Dr. Khazanovich opened with, it's a great time to be a pavement engineer. And thank you for being my therapy group today. As Tyler mentioned, we're going a little bit out of order. Fan Yin's flight is delayed and he'll be in this afternoon. So after me, Dr. Dave is going to present on some of the Flex Team sessions. A little bit of a, there we go. A little bit of a deviation from what was on the agenda, and especially what was on the agenda about a month ago. I am not Fan Yin, and I am not Raquel Moraes, who was supposed to be the speaker today on this topic from NCAT. Raquel has a upcoming surgery, and she's not able to travel. So changing the title a little bit. So I'm going to be overall providing a summary of the NRRA spray rejuvenator test sections and not diving into the chemistry as deeply as Dr. Moraes would. So if anybody here was really looking forward to 30 minutes of chemistry, I've got it down to about 5 minutes and I apologize. All right, so what is a spray rejuvenator, or what are these treatments? So they are for asphalt surfaces, and they're intended to restore binder properties and delay surface aging. They were originally developed in the 70s. Products have been on the market since then, but increased attention lately due to bio products being on the market, as well as the overall kind of focus of our industry getting more focused on preventative maintenance type treatments. So project objectives, I mentioned that these products had been around for a long time, but there's still a lot of questions in what they're actually doing, both in the short term and in the long term. And then what is that doing to our binder itself? And then how long does that last? And then from an agency or an owner standpoint, how can all this be measured in a kind of QA, QC type environment, and then ultimately for payment? So this originated kind of in the heat of COVID. It was 2020 when we first put out our initial call for products, and then construction was delayed until 2021. But that gave us a lot of lead up time into this study to get players and stakeholders on board. So this was just a general call for any products marketed in the general umbrella of spray applied rejuvenators. We did not do any pre-screening, and we did not do any selection of products to be in the study. It was basically, we are going to provide the real estate and the monitoring. If you have a product that's marketed in this general category, please join the study. So really want to acknowledge all of the manufacturer participants that made this happen by putting themselves out there and putting themselves into this study. And then we did not do any testing or evaluation of what is a rejuvenator or what are they actually doing to the pavements at this stage in the study. It's just general if you want to participate. That being said, some of the treatments we applied wouldn't be applied on the type of roadway surfaces. They were just added for beneficial type information. So products in the study, general couple categories that they're divided into, both a bio-based and then a petroleum-based. So where is the source material coming from? And then the group A, group B being with a fine aggregate application or with no fine aggregate application on there. Very different aesthetic appearances with each of these. I know I call this image the checkerboard. It's kind of hard to see, but there's basically from a white type fine aggregate that's placed on there to a very deep black surface. So a wide array of surface, just visual properties. So the test sections themselves, we had 12 different products included in the study, and they were applied at 3 locations. 2 of those locations, which are on MnROAD's low volume road, and those were applied in 50-foot stretches. So we will see those on the tour tomorrow. And then we also applied the same treatment in St. Michael, Minnesota, which is about 20 minutes away from MnROAD. And these were applied at 500-foot length or half a mile. So we get a bigger evaluation of the products. You can see in the image here, we measured during application, we measured the spray rate, so the applied application rate, as well as we had roofing felt at the edges of the test sections, trying to avoid contamination or spray over going from one section to the next, especially at MnROAD where we had everything more or less right on top of each other. In addition to the 12 treatments, we also had 2 controls at each of these locations as well. The controls were determined based off of where we were getting, or to avoid pickup and contamination from the adjacent treatments. So we had controls at both ends of the sections. All right, so now getting back into the overall contracting effort. This project was initially created through the NRRA, and then we had a slight delay with COVID. During that time, there actually was another project letting, or another project was awarded to Michigan State from the Minnesota Local Road Research Board. So what that did, it actually allowed us to have 2 separate research projects on the same test sections and study. And we were able to work with the TAPs and the scope of each project, and we're able to refine the scope of the contract that was let through the NRRA with NCAT. That one really focused on extracted and recovered binder testing. So chemical and rheological characterization from extracted and recovered binder testing from cores taken at MnROAD. And then with the Michigan State or Local Road Research Board contract, that was refined to focus on mixture testing and construction monitoring and field performance. And really, since that was through the Minnesota Local Road Research Board. All right, thanks for bearing with me on that. Like I said, now I'm getting into some of the results. Want to introduce what was collected. I've just got a couple snapshots of what's included here in the presentation today. The big takeaway from all of my kind of testing and results, the first takeaway is there's a lot of products in the study, and MnDOT did a lot of testing to make this project happen. And then second takeaway is that we have 2 reports that are going to be finalized in the next couple months. So the data I'm sharing is still under TAP review, but we'll have publications available in the near future. So friction was measured throughout the study in multiple different ways, friction and texture. So we did, you can see the box with the trail of water coming off of it is the dynamic friction tester. So that's a portable localized friction testing unit that we have. And then behind that, you can see sand patch circles as well from sand patch testing. And then the Michigan State team also took cores and tested with a British pendulum in the laboratory as well. Overall friction results, we did see a reduction in friction after 1 month of testing. The reduction was not seen after 1 year of testing. And then the big takeaway friction-wise is your initial roadway performance or condition is important to whether it can handle the spray treatment in the first place. If you're starting with a roadway that has marginal friction values, it's not a good idea or not a good candidate for these spray applied treatments. You need to have something that can absorb the slight reduction in friction and then bounce back the following year. So now getting into further Michigan State testing on cores. And again, thanks to Emin Kutai and his team for these slides. Just marching through relatively quickly, they wanted to do a in situ test or a test on cores taken from the study. They had trouble doing the modified BBR just with some of the size specimens. So they ended up using a larger BBR beam and a similar 3-point bending testing setup. So the results I'm sharing on the next couple slides are from their modified 3-point bending test. So there's some of the fabrication stuff. But cutting down the core samples from MnROAD, doing some aging on some of them. And then this is where it gets to the fun part, where the control is on the left, and then you have the different products on the right. So this is the 1 month or unaged cores, and then moving through to the 1 year. And then that red line coming across, and each of the different products changing from then. So at 1 year, we have everything, all this, the products, all the treatments showing reduced stiffness in this modified bending beam test setup. So similar for the lab aged or 2 years, as well as the lab age condition, where we're still seeing a difference in some of the treatments to the kind of extreme aggressive age condition. All right, so all products showed a benefit. So this ranking here was specifically asked for by the Local Road Research Board. And ultimately, product selection is based more on what's shown here in these rankings. And again, these are based off of the laboratory tests that they use. The analogy that I like to use as far as the rankings or the good, better, and best setup that we have here is kind of a jet fuel analogy. Yes, a jet fuel has the highest octane, has the highest energy density, but I don't think any of us are driving cars like this. There's a lot more that goes to the selection process than just what was considered in the study and in the lab study. So now getting to the chemistry portion that I promised, I relied on a lot of AI for help with my images coming up. Dr. Moraes at NCAT helped me. This is not Dr. Moraes. This is me asking Google Gemini to draw a chemist dressed as a construction worker fixing a road. So you can blame me for the chemistry that's included in this study. I was naive enough when we first came into the study that I thought, hey, we have all of these chemistry tools. Is there something we can test on the pavement that'll give us a quick answer that we can come back to in the future, test it again, and this will let me know, hey, this Rejuvenator is doing something. I learned something that I learned my freshman year in college. chemistry is complicated. Chemistry is tough. The Raquel and the NCAT team do a really good job of telling you what these different, whether it's a triglyceride fatty acid or a glycol ether, they do a good job of explaining what each of those components does in an asphalt mix. She did a good job of making the report concise. And now it's kind of my takeaways from that. So bear with me. You guys have probably seen Chemistry for Dummies. This is Chemistry from a Dummy. Raquel did approve these, but this is kind of my crude takeaways of asphalt chemistry. So we did Serra analysis or fractionation of the asphalt into saturates or aromatics, resins, and asphaltenes. I always get confused with asphaltenes and maltenes. I have to remind myself that I like maltomeal cereal. So the maltomeal is good. So that's the maltenes. Those are good. And then the asphaltenes is where it gets bad. They're the heavy, long, black hydrocarbons. So be glad that I'm not helping make lunch today, but I had some fun with Google Gemini, kind of showing okay, with our maltenes being good, black marshmallows being the asphaltenes, and then showing that as it ages and and it's really the ratio. It's not necessarily the quantity, but it's how that ratio of the two changes from the unaged to the aged asphalt. So like I said, chemistry is complicated. Adding into that, you add your polymer modification. So you have the spaghetti noodles into that as well. And that was one of the things that came out in the study with both the Michigan State efforts as well as the NCAT binder analysis. Different base binders accepted the different products differently. So the PG, the modified PG H -34, it's an SBS modified binder, didn't really show a lot of improvement with these spray rejuvenator products because of kind of the chemistry that was existing, and then it already had good low temperature performance properties in the binder itself. And then adding to that complexity is each one of these different treatments behaves differently on what it's doing to the chemistry. So generally speaking, your petroleum-based are going to be directly adding maltenes, whereas your bio-based do more of inhibiting the aging or the conversion of your maltenes to asphaltenes. So big difference in the base binder type and then how the different products interacted with that. All right. Summing it back up for the initial takeaways. So we did see a slight reduction in the initial friction and reflectivity, and then those properties were brought back a year later. Again, all products in the study showed benefits. Proper characterization of your initial roadway is important. And then manufacturers and suppliers are the experts on their products. It is in their best interest to use those appropriately, and they have a lot of knowledge and will put effort to get that accomplished. And then selection depends on a lot more than what was included in the study, like cost, aesthetics, and then ultimately environmental considerations like EPDs or the source material. Additional testing and monitoring. So like I said, we did a lot of testing, we being the MnROAD team. So there was over 860 sand patch tests, over 430 different DFT tests. We did skid trailer testing, albedo. There's drone videos. I want to make sure everybody, from all the sections we've showed today, a lot of the images overhead were drone images. There's a YouTube link for those. Jacob Calvert works with MnDOT Aeronautics to capture those. And then lastly, this is a correct number, we have close to 2,000 cores taken from these sections. So we're just looking at that top ½ inch of asphalt. So we're taking a full depth core, cutting away to that top ½ inch, and then doing the testing on that. And then recently funded, we have a phase 3 of this study, or a 36-month testing selected through NCAT as well. I found an old project picture. So back when Emil and Glenn and Jeff Brenner were on the team here at one of our field sections in St. Michael. Really want to spend some time on this slide. So St. Michael, the city of St. Michael, Steve Bott gave us the location, the MnROAD team doing all the testing. District 3 of MnROAD does a lot of our traffic control and keeps us safe when we're out there. Then the research teams themselves for the slides. all of you with the NRRA TAPs and reviewing these sections. And then MnDOT Research and Innovation and Consultant Services. I don't know if any of them were able to make it today. Big thank you with all of our NRRA projects and efforts to this group. It's kind of behind the scenes, but they're the ones that really get the contracts and the money and everything flowing. So thank you to any of them as well. All right. So that is all I had.
Thanks again, Michael, for that excellent presentation. So I'm going to turn it over to Kurt because we're going to have a little change of our agenda today.
Okay. Yeah. Okay, so we're going to move up one of the presentations from the flexible team now. So we're going to hear a presentation here from Dr. Eshan Davy, and Dr. Eshan Davy is a professor and graduate program coordinator of civil and environmental engineering at the University of New Hampshire. Eshan's research and teaching focuses on performance-oriented design, material selection, and management of pavement infrastructure. Eshan's presentation is titled Sustainability Aspects of the 2022 MnROAD Reflective Cracking Challenge. Please welcome Dr. Eshan.
Thank you, Kurt. So again, I'm not Fanian. I wish I was. He's a great speaker, great researcher. He's on his way, as I understand, so we swapped the presentations. No AI in this presentation, sorry. It's all human-generated content in this particular presentation. It's truly in spirit of NRRA. It's really a team presentation. I'm just presenting it here. You'll see about a third of presentations really put together by Michael, about a third of it put together by Suri and Ben from Auburn and NCAT, who are partners on this project. And then the last bit that you'll see is generated by us. I'd also like to thank Heritage Group. They are also partner on this particular project, on this effort that I'm talking about today. They didn't have a role in that, so that's why I didn't put any names from Heritage on this slide. So I am between you and lunch. I'll try my best to get you to lunch on time. I'll start by just giving a very quick overview of the MRCI study itself, just a refresher. I think many of you have seen that content. Go a little bit more, spend more time towards the second, third, fourth items here, which is really what I've been asked to present, which is task 5 in this project. MRCI itself is really conducting life cycle assessment on the mixes that were used in MRCI study, as well as the performance side of things. We haven't gotten to the performance side yet. This winter or spring was the first one where we actually have reflective cracks now. So we'll be working on it. So this will really focus on cradle to gate analysis, comparing the mixes with different type of additives, and then also some A4 and A5 stages of life cycle, which are transportation and construction itself. So in terms of overview of the project as a whole, the main idea here is to provide a tool to NRRA members and to pavement community in general that they can use in selecting their overlays as they are rehabilitating their existing asphalt pavements, and also provide that tool that can conduct some cost analysis as well as overall impact analysis. So it somewhat mirrors one of the first projects done through NRRA in phase 1, which really worked towards developing and exploring asphalt overlay options or solutions on rigid pavements. This part really focuses on asphalt. As common with NRRA, you heard in previous presentation by Michael, we are once again trying to do 2 for 1. So really, MRCI project has quite a bit of overlap with an additive group experiment, which is really a pool fund approach, a joint effort between NCAT and MnROAD, and MRCI sections and additive group sections are really overlapping. 8 out of the 10 sections are used in both those studies. Now, in order to develop a tool that really allows you to make some recommendations, the idea here is to look at how your life cycle comparisons looks between different type of mixes and also in terms of what's underneath. In order to do that, we have to have life cycle assessment. And more importantly, we have to have life cycle assessment that's not limited to cradle to gate or cradle to constructed, but also considers performance. And that's the main message that I want for you to take away from the presentation, because again, here presentation, we are only going to be looking at A1 to A5 stages. The remaining stages are coming. It's just that the performance is now, the differences are now showing up. So hopefully in future, we'll be able to present that as well. So overview of Mercy study, 10 sections. I'll talk more about the cross sections, but they are all on the Interstate 94 on the main line, and all of them are constructed with flexible pavement underneath and then an overlay on top. So the way the construction is done was first by constructing 5 inches of really bituminous base, 58S minus 28 mixture, a standard MnDOT mix. And then there were saw cuts made in half of the section. So you can see down below, 400 feet section, 200 feet, the underlying layers are intact, and the other half has saw cuts. Those saw cuts are full depth in order to really create the worst case type of scenario. Leaving stuff intact also has its own purpose. As we saw in the previous efforts done at MnROAD, thermal cracking, low temperature cracking, obviously a big challenge. And so we have this nice half of the section that really is dedicated to thermal cracking, and another half of the cells are dedicated to reflective cracking. So after those 5 inches were constructed, saw cuts were made. When saw cuts were done, inch of top layer was milled off in order to create that layer that you would typically have on your asphalt on asphalt type of overlay jobs. Granted that this old asphalt here is not aged as we would often have in many of the real highways. And then there's 2 inches of unique surfaces put, 10 different cells, each one with different type of mixes. So the type of mixes, there are really 3 controls. 2 of the control really compares if you're familiar with Minnesota lingo, then B oil with C oil. So you have 58S minus 28 versus 58H minus 34, where the H minus 34 is polymer modified, in this case, SPS modified. Then we have additive sections. 2 of them uses 2 type of aramid fibers. To suppliers of aramid fibers, and you'll see the names of suppliers and so on in coming slides that are done with this polymer modified binder. We also have a control section that's done with approximately 49 minus 34 binder, essentially something that would be comparable to this binder without modification. So the low end is still minus 34 there. And those are used on 2 of the dry additives, where dry plastic additive and dry rubber additives are used. And then finally, there are 2 blended wet plastic and wet rubber additive. As you saw in Dr. Yu's presentation, the wet rubber additive is actually comparable to that same system. And then lastly, there's SuperPave 5 section. SuperPave 5, because that showed very good performance in the first NRRA study on reflective cracking, where we had asphalt overlays on rigid pavement, and that was the reason to also include that in this particular study. So all of these mixes are designed at the level 5, which is 10 to 30 million E-cells, 12.5 millimeter SuperPave design. All of them have 20% wrap in it. This just gives you a little bit more information on exact modifier or exact additive types. We'll come back to it as I go through presentation, but just for completeness, I included that in the presentation here. The pavement life, it's really your life cycle. We have different phases in it. And I think by this point, most of us in room have seen images something like this, with all the effort that's been going into things like low carbon materials, life cycle assessment, development of PCRs to generate EPDs. And so if you look at A1, A2, A3 stages. That's what we typically call cradle to gate type of LCA, and that's what lot of current effort on PCRs in order to generate EPDs has been focused on. A4, A5 stages are really transporting that material and then the construction itself. B is a phase that still exists mostly in the research domain. In this project, we will use it, and you'll see why when we come to the end of the presentation, because that's where a lot of these distinctions, especially these type of innovative modifiers, show the differences in terms of what your embodied carbon amounts could be when you consider the operational side as well. So scope of LCA work within the context of MERCI is to start with obviously cradle to constructed, because that's the data that we already have from the construction, and there's certain life cycle inventories that had to be developed. And now in future, we'd like to extend it into use phase as well. So this presentation will just focus on A1 through A3 and then A4, A5 stages. When we talk about mix specific comparisons, we did it just in terms of tons. So we'll look at what is the global warming potential per ton of these different mixes. And then when we are looking at A4, A5 stages, the functional unit there is really the construction of those test sections itself. So 450 feet, 29 feet wide, 2 lanes and shoulders. So that's the functional unit used here. Now, to do LCA, obviously, we need inventories or we need data. And there's foreground data, background data, foreground data specific to project collected for these particular mixes, for these cells. Background data would rely on existing EPDs if a manufacturer already has environmental product declaration on it. So foreground data collection, mostly coming from the QC data, additive group experiment required or was part of that experiment that NCAT had their testing trailer available here, and they conducted a lot of testing on those 8 of the 10 mixes that were part of additive group, including also taking measurements on how much fuel was used at hot mix plants, how much electricity was used at it, so that we can really make a fair comparison between different mixes. So the trailer was here and they tested 8 out of 10 mixes. In this presentation, I'll focus on those. Right now, we are working with also using the mix design data and the test summary sheets in order to also do similar analysis with the 2 sections that are solely just part of MERCI and not part of additive group experiment. So just to show small differences do have to be considered when you're looking at conducting LCA. So just changes in binder contents or even looking at in-place densities, because that impacts how much mix actually gets moved there, what are the thicknesses that you end up with. All of that goes into your calculation. And so having those are important. And that's why oftentimes I get asked, especially as I'm talking to students about why is it taking so long for construction industry to settle on product category rules? There's a lot that goes into it, right? It's not as simple as a standard automotive manufacturing process where every pickup truck is manufactured same way. They all use same amount of metal and so on. So it's much easier to do. In our case, as you'll see, even between these 450 feet sections, there are differences in terms of how much fuel gets used, how much compactive effort goes into compacting them. And all of that translates into differences in terms of what your final global warming potentials are. The background data, a lot of these additive mixes use additives. And while now with things like NAPA's Eco-Emerald label system, we have existing PCRs or EPD processes for standard asphalt mixtures, it's still a work in progress when we look at these additives. So this is showing which databases were used. Specifically when we talk about the binder itself. So the Asphalt Institute LCA study generated a lot of information, and for 3% SBS modified binder for the 58H34 and just the control binder, that's the database that we utilized. When it comes to dry rubber, the Smart Mix, the technology, there's actually LCI was a work done between NCAT and Smart Mix, where 6-month data from their Georgia facility was used to develop the life cycle inventory, and that got used in this study. The challenge is dry plastic. There's not really existing EPDs for how that gets incorporated in. I know right now there's multiple working groups that are ongoing between NAPA and Asphalt Institute that's trying to fill those gaps. So we had to rely on some external data sources that were closest to those kind of materials. And then certain additives, the manufacturers are very proactive, both Forta and ACE or Forta and Surface Tech. They both have EPDs for their aramid-based fibers, so those were straightforward. We could directly use the EPD. It's gone through the ISO process. We know that those are already vetted through, and we just directly utilize those. In terms of data collection during manufacturing, so Suri specifically from NCAT actually had a lot of data collection effort during the construction with use of flow meters on the natural gas that was used at the CS McCrossin plant, as well as electricity. And so that was measured when each mix was produced. So we know how much gas went into production of each individual mixes. And that's very helpful because we can, as you see on the next slide, we can really then look at how much energy was used in producing these. And again, these are all normalized with respect to a ton of mixed production. You can see some of them, one that we'll see later on as well is wet rubber, much higher natural gas requirement. Part of it was to do with the oil heaters used in the tanks to keep that binder more flowable and maintain the sufficient viscosity. So when we package all of that together in terms of just the production stage, that's cradle to gate, there's really what it looks like. So the first part is your control. That's your, in this case, 58H minus 34 treated as control for the additive group experiment, and then all the unique mixes after that. And the numbers on top are really showing what is the percent change with respect to that control itself. Okay. And this is in terms of your global warming potential, so kilograms of CO2 equivalent greenhouse gas generation per ton of mixed production. So what we first of all see is anytime we look at unmodified binder compared to that modified binder, you see a drop, and that makes sense. SPS as a polymer has a fairly high embodied carbon content that goes into creating it, and then also the blending process and everything else. So you do see a benefit when you are using unmodified binder in terms of that CO2 generation just in the manufacturing process. We look at same thing with the dry rubber as well, because that also used an unmodified base. And although wet rubber used modified binder, it actually had a comparable or slightly lower number as compared to the modified, mainly because of that high propane or natural gas use at the plant. So it kind of made up the difference there. Same thing with wet plastic. Again, it used unmodified base binder. You are seeing that 12% drop coming as compared to the control, and whatever binder is replaced with the LDPE itself, you are accounting for that as well. And then mixes that were all done with the modified binder, not much difference. I mean, at most 1% difference off of control. So you're not really seeing any difference from those additives in terms of just the construction process itself. And that's good because oftentimes people are not sure, and it's like, okay, I'm adding this new compound into my mix. Is it going to all of a sudden increase what type of global warming potential I'm creating? So that's A1 to A3. Now let's look a little bit at A4 and A5 stages, which is really the transport to site and construction, mainly construction transport to site. All of these went same amount of distance from the plant to actual construction. There is small change though, I'll talk about it, and that has to do with just the inherent GMM difference or the density of mix itself, because that controls how much mix you are actually moving to the site for a given thickness. So once again, foreground data collection, all Caterpillar equipment, Todd. So we had Suri once again on site noted down the actual serial numbers for the equipment, and as well as the operation time and dwell time or idle time of these construction equipment, which allows us to then translate again into what type of fuel usages they had. That translates into what type of emissions were generated. So again, a lot of data collection effort went into this. Also, the thicknesses, and I'll come back to thickness because that's something that we do need to improve upon as we redo this analysis. So I don't expect you to really go through this whole table, but it's essentially showing what was the operating time versus idle time on each of these pieces of equipment that were on site between your material transfer vehicle or device shuttle buggy versus paver, static, pneumatic, and vibratory rollers for each of those cells, and also the fuel consumption rates for these equipment based off of the actual model number and the data that manufacturers have published. And then that can be converted into things like the amount of energy that they utilize during the actual construction process. So we combine all of that. Additional foreground data, as-built density, that matters. That matters because that's directly tied to how many tons of mix you are actually bringing to site, and how thick your layers are is also a factor that matters. If you have thickness differences, that will show up in your LCA. Now, this is something, as I mentioned, we'd like to redo it with maybe a core-based data or additional data. Initial analysis was done with just estimates that were done with some dielectric-based measurements, and that's one area that can be improved. But overall, you can see not so much of thickness differences as predicted from or estimated from the GPR. So what do the results look like? And a big thing that I'd like to bring here first is the construction phase impacts are actually much smaller numbers compared to the mixed production itself. Mixed production itself, this axis was between 55 and 60 kilojoules per ton of mix, right? Here we are looking at, for the whole section construction, between 250 and 300 kilograms of CO2 equivalent, about between 120 to 130 tons of mix in order to do all of those sections, right? So if you really convert those A1 through A3 numbers, you are conservatively looking at between around 60,000 kilograms of CO2 equivalent, versus here we are only looking at 250 to 300. So it's really a small fraction of your cradle to constructed difference. Still, we can see some differences between the sections. The fiber section, for example, and the 4934 control, those two are showing higher numbers, and most of that is coming from two things. Small differences in the GMM of the mix itself, as well as what type of static roller operational times were needed. So how compactable your mix is does have an impact as well, because that controls how many passes you are going to need to do to get to a certain air void level. So just to summarize, A1 through A3, big things that we learned: modified base binders, they had quite comparable environmental impact to those that was and modified here, as in with use of plastics or rubbers or fibers, compared to the polymer modified control. Mixes that had the unmodified base binders, especially the two wet ones, usually showed about 9 to 12% lower impact, mainly because the base binder itself was unmodified and didn't have that 3% SPS. Overall, if you look at it in grand scheme of things, little to no impact in terms of the differences between those 8 unique mixes. And that's good. That at least takes some of the fear out, that if we are doing some kind of a new process, we might be all of a sudden increasing what kind of global warming potential we may have. And then from the construction side, when you compare to A1 through A3 stages, that's where most of your impacts are. A4, A5, very small numbers compared to the overall production itself. And where the differences were, they're mostly coming from in-place density effects as well as the compactive effort effects. So those are the two things that seem to be impacting most. So coming back to what I said earlier, I think the biggest thing that that we learned by going through this is I think the differences in terms of overall LCA is in performance, not necessarily these differences and how these mixes are put together and manufactured. And that's the next step that we are looking forward to. We'd also like to go back and fix some of the data gaps that we had in LCA data. So that's ongoing right now. And also to give update on overall project lab performance testing on these mixes. We are done. We are just awaiting one set of testing from Illinois DOT. Otherwise, it's done. We plan to send that task report out to TAP pretty soon. Same thing with performance modeling. Most of it is already completed. And field performance, that's starting to come in now. As I mentioned, this spring is when we started to see differences between the 10 sections. And if you follow the YouTube channel, you can also see the videos of all the Mercy sections there as well. I also have a couple of pictures in the acknowledgements and the thank you slides. So a lot of people to acknowledge. Obviously, all the MnDOT and MnROAD team for tremendous amount of data collection, the construction, everything else. Folks who really help with that foreground data collection with both with Martin Marietta as well as CS McCrossan, and then NCAT team who was on site for gathering all of that information, like what were the equipment operational time versus lag times and idle times and so on. So with that, I'd like to thank you for your attention. Just two pictures here, cell 2230, which is 58S minus 28. It did undergo some cracking this past winter, and then contrasting it with the very last cell, which is 2239. You can see this crack in shoulder, but very faint, maybe no crack going through the actual overlay itself. So would like to present more information on that, maybe at a later NRRA meeting to show the performance differences and then how that impacts LCA. Thank you.
Excellent presentation, Eshan. And any questions?
I honestly do not remember, but it was essentially from the CS McCrossan plant to MnROAD facility. So it's, I don't know what that, yeah, roughly that much. Now, one thing I didn't cover, but A1 through A3, there was some differences in haul distances of the binder itself to the plant, and that was considered in the A1 through A3 because some of it was supplied by Flint Hill and other was from Matthew, and so that difference does go into the calculation. There's another one up here, Ben.
Is the entirety of the global warming potential calculated in A4 and A5? Is that just the fuel consumption, or is there something else?
A4 and A5 is predominantly, would be just the transportation of the mixture and the placement are the only phases. So it'll all be reverted back to diesel consumption only.
Good question. All right.
Thank you.
We are doing some work similar like that. But I have a question: is that all the construction equipments are the same for all the sections?
Yeah.
Okay.
Yeah. Same
So
construction.
Contract, the same contract.
Yep. Same contractor, same construction.
That tells the
Yeah.
It's a different contract.
You will see differences. Yeah.
Exactly.
Yep. 100%. Thank you.
Thank you.
Thanks.
Those that are presenting after lunch, you please bring your presentations up front. We got voted. And lunch will be ready.
Let's ready. I have a couple.
Ready? Enter that door down there and work your way this way back to the table.